The term observable universe defines the physical limit of what we are able to see and measure. It does not represent the entire universe, but only the region of space whose light has had time to reach us since the beginning of everything. When we say that the universe is about 13,800,000,000 years old, we are talking about the age of time, not the maximum distance we can see. Space has been expanding since the initial moment, and therefore, the light that left from very distant objects 13 billion years ago traveled through a universe that continued to expand during its journey. The result is that the radius of the observable universe is much greater than the light travel time would suggest, about 46 billion light years in every direction. This means that the total diameter of the sphere we can observe reaches approximately 92 billion light years. This limit is not defined by instruments, but by the laws of physics. No telescope, no matter how advanced, can observe beyond this horizon because there simply has not been enough time for the light from more distant regions to reach us. Even if we waited billions of years, we would still be limited. Space expands faster than light can cross it. There are regions of the universe that are already moving away from us at speeds greater than that of light, not because they are moving through space, but because the space itself between us and them is expanding. This creates a natural boundary called the cosmological horizon. Everything beyond it exists, but it can never be observed or reached. Within this limit, the observable universe contains at least 2 trillion galaxies. Each one houses hundreds of billions of stars and probably trillions of planets. Even so, the volume accessible to observation is only an infinitesimal fraction of the total cosmos. The real universe may be much larger, possibly infinite, but this hypothesis can never be proven because there is no way to see beyond the light horizon. Astronomical observation is based on photons, and no photon coming from outside this limit can reach us. When looking at the night sky, everything we see, every star, every galaxy, every luminous point, is within this observable bubble. The most powerful telescopes, such as the James Webb, capture light that left galaxies formed just over 300 million years after the Big Bang. This means that we are seeing the past on a cosmic scale. When a star is 1,000 light years away, its light takes 1,000 years to reach us. Looking at it is looking back in time. The observable universe is therefore a window into the past. What we see today may no longer exist. This limit of observation has profound implications. It defines not only the reach of our knowledge, but also the nature of our ignorance. Everything beyond the horizon is inaccessible, and in a sense outside of observable reality. Even the physical laws may vary in regions we will never see. This means that science, no matter how advanced it becomes, will always be local, restricted to what light allows us to know. The observable universe is, then, the stage where cosmic history unfolds before us. It is the volume in which light has had time to travel since the origin. Within it are all the galaxies we can study, all the civilizations we could detect, and all the matter that interacts with our instruments. Beyond it, there is absolute silence. This notion redefines what we mean by seeing. When we say we observe the universe, we do not observe the present, but the accumulation of light that has arrived until now. Every photon that reaches our eyes or senses is an ancient message traveling for billions of years through expanding space. Thus, what we call the visible universe is, in fact, a luminous memory of the cosmic past. Understanding the observable universe is also the first step toward realizing why we will never leave the Milky Way. If we cannot even observe the entire universe, we could not possibly travel across it. Light sets not only the limits of vision, but also those of practical existence. We are observers trapped inside a sphere of information that expands faster than any attempt to escape. In the end, the observable universe is the frontier between what is real for us and what lies beyond the possibility of perception. Everything we know happens within this bubble of light, and everything that exists outside it remains, by definition, eternally invisible. Understanding the distances within the Milky Way is the first step toward realizing the size of the abyss that separates humanity from any real possibility of crossing it. The human mind was not made to intuitively handle numbers of such magnitude. When we speak in kilometers or even in millions of them, we can still imagine an approximate scale. But in the universe, the most common measurements are not in kilometers, but in light years. the distance that light travels in 1 year, moving at about 300,000 kilometers per second. In a single second, light could circle the Earth 7.5 times. In 1 year, it travels nearly 10 trillion kilometers. This is the minimum unit astronomers must use to deal with the space around us. The Earth orbits the Sun at an average distance of 150 million kilometers, which equals only 8 light minutes. This means that the sunlight warming our planet left the Sun just over 8 minutes ago. Within the solar system, this scale already grows quickly. Light takes about 40 minutes to reach Jupiter, and more than 5 hours to reach Pluto, which marks the edge of the main planetary region. The Voyager 1 probe, the most distant human-made object, is more than 20 billion kilometers away, about 20 light-hours distant. Even so, in galactic terms, it has not yet taken even the first step beyond the cosmic backyard. The solar system occupies a tiny region of a spiral arm of the Milky Way called the Orion Arm. This arm is a structure filled with clouds of gas, young stars and nebulae, stretching across thousands of light years. The entire Milky Way is about 100,000 light years in diameter. This means that if we could travel at the speed of light, it would still take 100,000 years to cross it from one end to the other. No physical object, not even the fastest ever created, comes close to that scale of movement. The distance between the Sun and the Galactic center, where the supermassive black hole Sagittarius A star resides, is approximately 27,000 light-years. That equals 250 billion kilometers. It is a distance so great that if a spacecraft traveled at 10,000 kilometers per second, far beyond any real technology, it would still take more than 80 million years to get there. Even a ray of light, the fastest known phenomenon, takes 27,000 years to cover the path between the Sun and the nucleus of the Milky Way. The Sun, and all the planets that accompany it, orbit this galactic center at an average speed of 220 kilometers per second. Even so, to complete a single revolution around the galaxy, it takes about 250 million years. Since the Earth formed about 4.5 billion years ago, the solar system has completed just over 18 orbits around the galactic center. Each revolution is slow, constant and imperceptible, but it is what keeps us bound to the gravitational structure of the galaxy. These proportions reveal how confined our existence is. Even the nearest stars are far too distant for any significant movement on a human scale. Alpha Centauri, the closest star system to the Sun, is just over 4 light-years away and 40 trillion kilometers. With the speed of current probes, a trip there would take more than 80,000 years, and that would only be to visit a neighboring star within the same galaxy. When we look at the night sky, most of the stars we see belong to our immediate neighborhood, a small fraction of the galactic disk. Even the most powerful telescopes that observe stars in other parts of the Milky Way do not capture individual distances. They record diffuse brightness from billions of combined stars. This is the scale of the Milky Way, an ocean of light in which each star is a lost grain of sand. To comprehend these distances, scientists use analogies. If we reduce the Milky Way to the size of a country, the solar system would be smaller than a human cell within that space. The Earth in turn would be an invisible dot, and all the signals of our civilization, the lights, transmissions and machines, would be completely lost in the cosmic noise. This is the true scale of the distance between us and the center of the galaxy, a path that not even light travels instantly, a space so vast that time itself dissolves within it. Every measurement used in astronomy is an attempt to translate the incomprehensible into numbers. But in practice, there is no intuitive way to visualize what 27,000 light-years truly means. It is an interval in which entire civilizations could rise and vanish before a single ray of light completes the journey. To understand this scale is to understand why there are no realistic plans to leave the Milky Way. It is not a matter of choice, but of proportion. Distance is the universe's language to remind us that everything we do happens within a minuscule portion of space. And even when we look at the bright center of the galaxy, we are seeing light that left there when the first living beings on Earth did not yet exist. The Sun occupies a relatively discrete position within the Milky Way. It is situated in one of the smaller spiral arms, known as the Orion Arm, an intermediate band of stars, gas, and dust that stretches between two main arms, the Sagittarius Arm and the Perseus Arm. This location is strategic from a cosmic point of view. We are far enough from the galactic center to avoid the denser and more violent regions, where black holes, massive stars, and supernova explosions make the environment unstable, yet not so far that we are isolated in the outer space of the galaxy. The Milky Way is a barred spiral galaxy, composed of a dense core of old stars, a central bar that crosses this core, and several spiral arms that rotate around it. It measures about 100,000 light-years in diameter and about 1,000 light-years in thickness in the region of the main disk. This structure is sustained by a balance between gravity, which tries to pull everything toward the center, and rotation, which pushes matter outward. The result is a flat, rotating disk with a bright core and arms that extend in gentle curves. The Sun orbits the galactic center at a distance of approximately 27,000 light-years. At this distance, the density of stars is moderate. There is enough room for planetary systems to exist stably without intense gravitational disturbances. This region is considered a cool galactic habitable zone, where the conditions are ideal for the development of life. Being closer to the center would mean constant exposure to radiation, supernova explosions, and gravitational interferences. Being too far would mean living in a region poor in heavy elements, which are essential to the formation of rocky planets and biological organisms. The Milky Way contains between 200 billion and 400 billion stars. Recent estimates indicate that it also harbors trillions of planets. Many of these worlds orbit stars similar to the Sun, scattered throughout the spiral arms. Even so, the immensity of the galaxy is such that, even if we traveled at the speed of light, it would take 100,000 years to cross it from end to end. And since nothing with mass can reach that speed, in practice we are confined to a small fraction of it. The thickness of the galaxy is another impressive fact. Although the main disk is about 1,000 light-years thick, there is a region called the Galactic Halo, which extends for tens of thousands of light-years above and below the central plane. This halo contains ancient stars, globular clusters, and a large amount of dark matter, an invisible substance that makes up most of the galaxy's mass, and whose gravity holds everything together. The influence of the halo causes the Sun and the solar system to move in a slight vertical sway, oscillating above and below the plane of the galaxy every 60 million years. The Milky Way also has a central bar of stars that cuts across its core. This structure is a kind of gravitational corridor that channels gas and dust toward the center, feeding the supermassive black hole, Sagittarius A. The core, in turn, is a dense and turbulent region where radiation is intense and new stars are constantly being born. Because of this activity, the galactic center is inhospitable to life as we know it. Our current position, far from this zone of chaos, is a favorable coincidence that has allowed Earth to exist in relative stability for billions of years. Seen from afar, the Sun would be just another indistinguishable point of light among hundreds of billions. It and its planets revolve around the galactic core at a speed of about 220 kilometers per second, completing one revolution every 250 million years. This means that since the first dinosaurs appeared on Earth, the solar system has completed only a single full orbit around the center of the Milky Way. This temporal and spatial scale reinforces our smallness. The solar system, despite being the center of all our observations and stories, occupies a tiny space within the galactic structure. If we could shrink the Milky Way to the size of the American continent, the Sun would be somewhere between the interior and the edges, and the entire solar system would be smaller than a microscopic cell. This intermediate position is, in a way, the reason we exist. We are far enough for the environment to be calm, yet close enough for the elements essential to life to be available. It is a stable location within a colossal structure. The Milky Way is not just the backdrop of our existence. It is the matrix that defines where and how it is possible. To understand the position of the Sun within the galaxy is to understand the setting in which life arose. It is to recognize that our civilization, our stars and our history take place within a tiny fragment of a system in continuous rotation. And even if we can never see it from the outside, the Milky Way is the place to which we belong, the fixed point within which our entire trajectory unfolds. Traveling within the galaxy and leaving it are two ideas that may seem similar at first glance, but represent completely different scales and challenges. Exploring the Milky Way means moving among stars that share the same gravitational field, within a structure that is united and balanced. Leaving the galaxy, however, means breaking that field, escaping the collective force of billions of stars, and crossing an almost completely empty space where the laws of physics impose absolute isolation. They are two distinct levels of motion, one possible only in theory, the other, in the current state of human knowledge, absolutely unattainable. Within the Milky Way, all stars orbit the same gravitational center, the supermassive black hole known as a star. The Sun, for example, moves around that nucleus at about 220 kilometers per second. Even at that impressive speed, it needs 250 million years to complete one orbit. This means that stars and planetary systems move within a shared field of forces, which makes it theoretically possible to navigate between them, provided there is enough energy and time. Navigation within the galaxy is a problem of scale, but still within a cohesive gravitational environment. Leaving the Milky Way, however, is something entirely different. To do so, it would be necessary to exceed the galactic escape velocity, estimated at about 500 to 600 kilometers per second. This is the minimum speed required to overcome the combined gravitational attraction of all the stars, visible matter, and the halo of dark matter that surrounds the galaxy. For comparison, Earth's escape velocity is 11 kilometers per second, and the Sun's, within the solar system, is 42 kilometers per second. Leaving the galaxy would require energy and propulsion thousands of times greater than those used to escape the Sun. No physical system conceived by humanity could generate that energy continuously and stably. Beyond the energy issue, there is the problem of time. Even if a spacecraft could reach escape velocity, it would still take millions of years to reach the visible edge of the galaxy. The Milky Way is about 100,000 light-years in diameter. The Sun is 27,000 light-years from the center, which means the nearest edge is about 70,000 light-years away. This means that even at the speed of light, the universe's maximum limit, the journey would last 70,000 years. No biological organism, civilization, or known technology could sustain a voyage of that duration. Traveling within the galaxy, on the other hand, although it may seem unattainable with current technology, is a far smaller challenge. The stars closest to the Sun are only a few light-years away. Alpha Centauri, the neighboring stellar system, is just 4 light-years distant. Compared to galactic distances, that is a short trip. The main barrier is not the destination, but the medium, interstellar space. Even on the shortest trajectories, the space between stars is an immense vacuum, with such a low density of matter that a ship traveling through it would encounter fewer than 1 atom per cubic centimeter. There is no fuel, no stopping points, no energy trails. Every movement must carry all the required energy from the start. The difference between traveling within the galaxy and leaving it also involves the question of the gravitational frame of reference. Within the Milky Way, everything that exists is bound to the same gravitational field. The energy required to go from one star to another is finite, although immense. But to escape the total field of the galaxy, the energy required tends toward infinity, because gravitational influence never completely ceases. It only decreases with distance. This means that in a universe dominated by gravity, there is no clear line where the galaxy ends. There is only a zone where its influence becomes imperceptible, but still present. There is also a conceptual difference. Traveling within the galaxy is movement within a stable and familiar structure. Leaving it would mean crossing a frontier into the unknown, intergalactic space. This region is an almost absolute vacuum, where galaxies are separated by millions of light-years. There are no visual references, no energy sources, no significant gravitational fields to guide navigation. It is a space where isolation becomes absolute. Even if it were possible to reach it, there would be no way to return. In summary, traveling within the galaxy is like moving inside an ocean whose currents are slow and predictable. Leaving it is like trying to leave the ocean and cross the void between universes. One is a technical challenge, the other a physical impossibility. The difference between these two concepts shows that no matter how much we dream of crossing the cosmos, our reality is confined within a space bounded by forces we cannot overcome. The Milky Way is not only the stage of human life, it is the system that defines its limits. Traveling between stars is to think on an astronomical scale. Leaving the galaxy is to face the very end of what is possible. Beyond the visible limits of the Milky Way stretches a vastness that defies any human imagination: intergalactic space. Unlike the interior of a galaxy, where stars, planets, and gas clouds are distributed in relative abundance, the space between galaxies is almost completely empty. It is a region dominated by darkness, extreme cold, and densities close to absolute vacuum. For every cubic meter of this space, there is, on average, less than one atom. It is an environment so rarefied that a spacecraft could cross millions of kilometers without encountering even a single particle. This is the true desert of the universe. The Milky Way is not alone. It is part of a group of more than 50 galaxies known as the Local Group. Among them are Andromeda, the closest and most massive, the Magellanic Clouds, the Triangulum Galaxy, and several other dwarfs scattered around. The average distance between the Milky Way and Andromeda is about 2,500,000 light-years. This is a measure so large that even light, traveling at 300,000 kilometers per second, takes 2.5 million years to cross it. It is the closest neighborhood we have, and yet completely inaccessible. Intergalactic space separates these galaxies like oceans of emptiness, and contrary to what the term emptiness might suggest, it is not static. The universe is expanding, and galaxies are moving away from each other at speeds proportional to the distance that separates them, a phenomenon described by the Hubble-Lemaitre law. This means that the farther away a galaxy is, the faster it recedes. Some move away at speeds so great that they already exceed that of light. This motion does not violate relativity because it is not the galaxy traveling through space. It is space itself that is expanding. This expansion creates an invisible boundary, the cosmic horizon. Everything beyond it recedes faster than light can travel. No signal, particle, or spacecraft can cross that boundary. Even if a civilization began a journey today, the destination would continually move away, making the voyage eternal and futile. Intergalactic space is not only vast, it is dynamic, and every second increases the distances between worlds. Between the Milky Way and Andromeda, for example, there is little visible matter. What exists are filaments of ionized gas and clouds of extremely tenuous hydrogen, detected by highly sensitive telescopes. In some stretches, there are regions known as tidal bridges, formed by the mutual gravitational attraction between galaxies that slowly pull matter from one to the other. However, outside these exceptions, intergalactic space is an environment where the density of matter is so low that it approaches absolute nothingness. Even the radiation that fills this space is weak. The main form of energy present is the cosmic microwave background, the thermal echo of the Big Bang, which today has an average temperature of about 2.7 degrees Kelvin, just above absolute zero. This radiation permeates the entire universe uniformly, but it is so faint that it represents only the remnant of primordial heat. There are no concentrated energy sources, no stars, and no significant gravity outside the influence of galaxies. Gravity, in fact, is what delineates the boundaries of intergalactic space. Each galaxy has a gravitational sphere of influence, within which its stars and systems remain bound. Outside that sphere, the pull is too weak to hold anything together. In the space between galaxies, gravitational forces practically cancel out, and objects that venture there follow solitary trajectories with no certain destination. Even light can travel millions of light-years without encountering an obstacle. There are also larger structures that shape this emptiness. Galaxies are not distributed randomly, but organized into clusters and superclusters, connected by cosmic filaments of dark matter and gas. Between these filaments lie immense voids, regions called sumvoids, which can span hundreds of millions of light-years in diameter and contain fewer than one galaxy per million cubic light-years. These voids represent true intergalactic space, areas where literally nothing happens. If we imagined a spacecraft departing from the Milky Way toward Andromeda, it would cross such a great distance that, in practice, it would never arrive. The expansion of space itself would increase the route during the journey. Even at the speed of light, it would take millions of years, and upon arrival, it would find a galaxy completely different from the one we observe today, because the elapsed time would have altered its structure. This shows that intergalactic space is not merely a path, it is a limit. What exists beyond the Milky Way is a universe that is moving away from us ever faster. A space that grows, where silence is absolute and motion leads nowhere. The crossing between galaxies is, from a physical point of view, a natural impossibility. The emptiness between them is not just distance, it is the definitive separation imposed by the very expansion of the cosmos. In summary, intergalactic space is the interval between the possible and the unreachable. It marks the practical end of exploration and the beginning of contemplation. It is the reminder that, even surrounded by trillions of galaxies, we belong to only one. And beyond it, the universe does not wait for us. It simply continues to expand. The speed of light is the fundamental limit of the universe. No object with mass can surpass it. This restriction is not a mere technological limitation. It is a direct consequence of the structure of space-time described by the theory of special relativity formulated by Albert Einstein at the beginning of the 20th century. According to this theory, space and time are not separate entities but dimensions of a single reality. Together, they form the fabric of the universe, within which all bodies and energy fields move. Within this fabric, light occupies a unique position. It is the fastest possible element because it has no rest mass. Photons, the particles that make up light, always travel at a constant speed, about 300,000 kilometers per second in a vacuum, regardless of the observer's motion. This constancy is one of the foundations of relativity. No physical experiment has ever detected variation in the speed of light, whether on Earth, in orbit, or in deep space. This invariance means that the very nature of space and time adjusts to keep light always at the same maximum value. When an object with mass tries to approach the speed of light, its kinetic energy increases exponentially. This causes its effective mass, what we call relativistic mass, to grow. In other words, the faster the object moves, the more energy is required to continue accelerating. At the limit, as velocity approaches that of light, the energy required becomes infinite. And since infinite energy does not exist, reaching or exceeding that limit is physically impossible. This is why no material body, no matter how small, can attain the speed of light. Another important effect of this law is time dilation. For an object moving at high velocity, time passes more slowly relative to a stationary observer. This phenomenon has been confirmed countless times, both in subatomic particles accelerated in laboratories and in atomic clocks moving in orbit. When a particle travels near the speed of light, its lifespan increases because, from its own point of view, time slows down. The same principle would apply to a spacecraft if it could reach such speeds. Time inside it would pass more slowly than outside. Yet the cost would be colossal energy and the continuous increase of effective mass, making movement more demanding with every additional fraction of speed. Light is therefore the absolute standard of speed in the cosmos. All other velocities, of planets, spacecraft, or particles, are measured relative to it. The structure of space-time is shaped so that nothing can surpass it. If it were possible to exceed it, the causal relationships between events would break. Cause and effect could reverse their order, and the natural sequence of occurrences would cease to make sense. The constancy of the speed of light is, therefore, what preserves the coherence of the universe. Even the boldest theories of modern physics, such as quantum mechanics or general relativity, respect this limit. Light is the frontier between what can exist and what remains impossible. There are phenomena that seem to exceed this value, such as quantum entanglement, where two distant particles appear to influence each other instantaneously. However, even these effects do not involve the transmission of information faster than light. They merely reveal a deep correlation between quantum states without violating the principle of causality. The speed of light also defines the concepts of distance and time in the universe. A light year, the distance light travels in 1 year, is the standard unit used to measure cosmic scales. When we say a star is 1,000 light years away, it means that the light we see today left it 1,000 years ago. This relationship makes the speed of light not only a limit, but also a cosmic ruler. It connects space and time in a single system of measurement. For scientists, this constancy is what makes the universe predictable. It ensures that the laws of physics work the same way everywhere. Without this limit, the structure of the cosmos would become unstable. If something could exceed the speed of light, space-time could distort chaotically, destroying the logic of motion and energy. The existence of an absolute limit is therefore not an arbitrary restriction, it is a condition of stability. On practical scales, this speed is so high that it seems unreachable, but on cosmic scales, it is insufficient to overcome the dimensions of the universe. Even traveling at the speed of light, it would take 100,000 years to cross the Milky Way and more than 2 million to reach Andromeda. The limit of light is therefore the frontier between dream and reality. It defines the utmost possible, and at the same time the impossible. Nothing can exceed the speed of light because it is the very rhythm of the universe. It is the way space and time communicate, the constant that sustains all known physics. To surpass it would be like trying to move faster than time itself, and time in the universe is not something to be overtaken, it is something to be lived. When we imagine a spacecraft approaching the speed of light, we enter the most extreme territory of physics. At that point, the behavior of matter, time, and even space itself changes radically. It is not merely about traveling faster, but about entering a different reality in which the laws of human perception no longer apply. As an object with mass accelerates, the energy required to increase its speed grows exponentially. This means that the faster it moves, the harder it becomes to accelerate it even more. At the limit, the energy required to reach the speed of light would be infinite, and its effective mass would also tend toward infinity. No machine, star, or civilization could generate such energy. But what would happen on the way to that limit is even more fascinating. According to the theory of special relativity, as speed increases, time inside the spacecraft slows relative to external time. This phenomenon, called time dilation, has been experimentally confirmed. Extremely precise clocks in airplanes, satellites, and subatomic particles show that time truly passes more slowly for bodies in rapid motion. If a spacecraft could travel at 99% of the speed of light, time inside it would pass about 7 times more slowly than on Earth. For every 7 years lived on board, 50 years would pass here. At that speed, visual effects would also be profound. The starlight ahead of the ship would undergo a shift to blue, a rise in frequency, while the light from the stars behind would shift to red, progressively vanishing. The field of view would contract, compressed into a luminous tunnel in front of the ship. The universe would seem to concentrate in a single direction, and the surrounding space would become dark. For the occupants, the cosmos would be transformed into a narrow, shining line where time almost stops. The surrounding matter would also become dangerous. Even dust particles and atoms in space, which are normally harmless, would become lethal projectiles. At speeds close to that of light, a single grain of sand would have energy comparable to a nuclear explosion upon colliding with the ship. No known material could withstand that kind of impact. Interstellar space, which is relatively safe at ordinary speeds, would become a field of constant destruction. Cosmic radiation, composed of highly energetic particles, would strike the ship with enough force to damage electronic circuits and destroy the DNA of any form of life. Furthermore, the energy consumption required to maintain acceleration would be colossal. Even with theoretically perfect propulsion sources, such as fusion or antimatter engines, the amount of fuel required would increase exponentially as the ship approached the speed of light. At some point before reaching it, the energy demanded would be so great that it would exceed the sum of all the energy produced by all the stars in the galaxy. Another inevitable effect would be the increase in relativistic mass. The faster a body moves, the more energy it accumulates, and that additional energy manifests as mass. To an external observer, the ship would appear increasingly heavy and difficult to move. At the limit, its mass would tend toward infinity. This increase would also affect space-time itself around it, creating perceptible gravitational distortions. If it were possible to continue accelerating, the ship would end up collapsing under its own energy, transforming into pure radiation before reaching the speed of light. From the crew's point of view, however, the experience would be paradoxical. Inside the ship, time would seem normal. Clocks, heartbeats, and conversations would keep a steady rhythm. What would change would be the external perception. While for the occupants the journey would last a few years, for those remaining on Earth centuries or millennia could pass. This is the so-called twin paradox, one of the most intriguing effects of relativity. In practice, no ship built from conventional matter could withstand the stresses involved in such acceleration. Material strength, heating from friction with the interstellar plasma, and the radiation generated by the compression of the electromagnetic field would render any structure unstable. Even if an ideal propulsion system existed, the biological, energetic, and physical problems would make the journey impracticable. These limitations show that the light barrier is not merely technological, it is natural. The universe seems to have been built so that light is the ultimate mediator of all interactions. Nothing surpasses its speed because nothing can transmit information, energy, or matter faster than it. This limit defines the flow of time and the order of events. If a ship tried to approach that limit too closely, it would not only face physical collapse, but also an extreme distortion of the reality around it. Space would appear to curve, time would almost freeze, and the notion of distance would cease to make sense. The journey would become a plunge into the very limit of the universe, the point at which physics, energy, and time become a single thing. That is why the speed of light is not just a barrier, but the structure that upholds the cosmos. To approach it is to touch the outline of reality, and to surpass it is something that, as far as we know, the universe does not allow for any being or machine. Time is not a fixed or universal entity. It shapes itself according to motion and gravity. This is one of the most revolutionary conclusions of Einstein's theory of relativity. Before it, it was believed that time was the same for all observers, a constant flow moving at the same rate everywhere. Relativity showed that this is an illusion. Time dilates, contracts, and deforms depending on the speed and the intensity of the gravitational fields to which it is subjected. Time dilation occurs because space and time are inseparable parts of a single structure, space-time. When a body moves very fast, the space ahead of it contracts, and time inside it slows down. This means that the greater the speed, the more slowly time passes for the moving object. This effect is almost imperceptible at everyday speeds, but becomes dramatic as one approaches the speed of light. A practical example is that of subatomic particles called muons, created in the Earth's atmosphere by the collision of cosmic rays. These particles have a lifespan of only 2 microseconds before disintegrating. However, muons moving at speeds close to that of light survive much longer, long enough to reach the surface of the Earth. For them, time is passing more slowly, which is why they can cover distances that would otherwise be impossible at rest. Time dilation has been measured and confirmed countless times, becoming one of the most solid predictions of relativity. Now imagine this effect applied to a spacecraft. If a ship traveled at 99.9% of the speed of light, time inside it would pass 70 times more slowly than on Earth. In practical terms, this means that while 1 year passed aboard, 70 years would pass for those who remained at home. This difference increases rapidly as velocity approaches the speed of light. At 100% of the speed of light, time inside the ship would stop completely relative to an external observer, something physically impossible since no mass can reach that speed. This phenomenon gives rise to what is called the twin paradox, a thought experiment that helps visualize the consequences of time dilation. Imagine 2 identical brothers. One remains on Earth, while the other travels through space at speeds close to that of light. When the traveler returns, he discovers that although only a few years have passed for him, centuries have passed on Earth. The traveler ages slowly. The brother who stayed ages normally. The paradox is only apparent. There is no physical contradiction, because the traveler's time really did pass more slowly. The difference arises because he experienced accelerations and decelerations that altered his timeline. This effect is not a theoretical fiction. It is accounted for in the navigation systems of satellites used on Earth. The clocks aboard GPS satellites, for instance, must be constantly adjusted to compensate for the difference between time in orbit and time on the surface. Time dilation, though minimal at low speeds, is already enough to cause significant errors if not corrected. What for us is just a small technological discrepancy, on cosmic scales becomes a temporal abyss. Time dilation shows that the universe does not possess a universal clock. Each observer has their own. The time of a star, a particle, or a human being depends on where it is and how it moves. This relativity makes the concept of simultaneity, the now, something local, not absolute. When we look into deep space, we see the past, because light takes time to reach us. With every galaxy observed, we are looking billions of years backward. The universe, therefore, is a collection of different times coexisting within the same space. From the perspective of a civilization capable of traveling at relativistic speeds, time dilation would be both an advantage and a curse. On one hand, it would allow reaching distant stars within a single lifetime aboard. On the other, it would mean that upon return the known world would have aged thousands of years. The price of the journey would be the definitive disconnection from one's own time. This relationship between motion and duration redefines what we understand as distance. When time slows for the traveler, the space ahead contracts. The stars would appear closer and the journey would seem shorter, but that is only an internal illusion. For the external universe, the trip would still last the actual time light takes to cross that distance. Time dilation is not a way to cheat the limit of light. It is the way the universe protects that limit. In the end, the paradox of relativistic travel is the clearest demonstration that time is not a straight line, but a malleable dimension. Speed does not just displace a body, it transforms the experience of time into something unique to each trajectory. And it is this fundamental deformation that makes interstellar travel so unfeasible. Even if it were possible to travel at extreme speeds, humanity could never maintain contact with the time it left behind. Time dilation is therefore the reminder that time and space are inseparable. Increasing speed is diving into another temporal reality, and the closer we approach light, the more the universe curves to prevent us from surpassing it. It is as if the cosmos protected the very flow of time, ensuring that no form of matter could ever escape it. Moving any body to a significant fraction of the speed of light requires such a colossal amount of energy that it surpasses everything humanity has ever produced or could ever produce with any known technology. This energy barrier is one of the fundamental reasons why large-scale interstellar exploration is unfeasible. The equation that describes this phenomenon appears simple, but is relentless in consequence. As the velocity of a massive object increases, its kinetic energy grows exponentially, not linearly. According to special relativity, the total energy of a body is given by the expression E equals gamma times mm times c squared, where m represents the mass of the object, c is the speed of light, and gamma is the relativistic factor, which increases rapidly as the object approaches the speed of light. When the velocity is small, this factor is almost equal to 1, and the increase in energy is modest. But when the speed reaches 90% of light, the value of gamma is already 2.3. At 99%, it surpasses 7, and at 99.9%, it reaches 22. This means that, to double the speed of a spacecraft, it is not enough to double the fuel. It is necessary to multiply the energy by absurd proportions. To grasp this concretely, imagine a spacecraft with a mass of 100 tons, a small mass by space standards. To accelerate it to only 10% of the speed of light would require the energy equivalent to tens of millions of hydrogen bombs. At 100%, the energy required would be infinite. Even theoretical technologies, such as nuclear fusion or antimatter, could not provide this amount of energy continuously and safely. The energy density required exceeds any known physical limit. Nuclear fusion, for example, converts only a small fraction of mass into energy, and even then it requires magnetic confinement and temperatures of millions of degrees. Antimatter, which would be the most efficient possible fuel, releases total energy in the annihilation of particles and antiparticles. However, producing a single gram of antimatter would cost billions of dollars and require more energy than it could itself release. Furthermore, storing it safely is practically impossible. Any contact with ordinary matter would result in immediate destruction. Another obstacle is the braking energy. Even if we managed to accelerate a spacecraft to a fraction of the speed of light, it would still need to decelerate upon approaching its destination. This would require the same amount of energy spent on acceleration, doubling the total cost of the journey. And in an environment where there are no available fuels or support infrastructure, all that energy would have to be carried on board from the start. The additional weight of the fuel would further increase the energy cost, creating a dead-end cycle known as the tyranny of the rocket equation. Even alternative methods such as solar sails or laser propulsion face severe limits. Solar sails depend on the pressure of starlight, an extremely weak thrust that only accumulates over long periods. To reach a meaningful fraction of light speed, A mirror several kilometers wide and made of material lighter than any known substance would be required. Laser propulsion, in turn, would demand an energy source capable of emitting unimaginably powerful beams for years without dispersion or loss of focus over billions of kilometers. Another critical factor is relativistic heating. As speed increases, particles of dust and cosmic radiation strike the spacecraft with ever-growing energy. At high fractions of light speed, the impact of a single particle could release enough heat to melt any protective shield. The energy required to maintain the structural integrity of the ship and dissipate that heat adds to the total cost of the journey. Humanity has already built machines that demonstrate the extreme cost of reaching relativistic speeds, particle accelerators. The Large Hadron Collider, for example, consumes enough energy to power hundreds of thousands of homes just to accelerate protons to 99.9999% of the speed of light. This is possible only because these particles have negligible mass. A spacecraft with billions of times more mass would require proportionally greater energy that simply does not exist on a planetary scale. Even if Earth were transformed into a single power plant, converting all solar energy it receives into propulsion, it would still not be enough to accelerate a single crewed spacecraft to a significant fraction of the speed of light. The Sun emits about 4 times 10 to the 26th watts per second. Harnessing that energy entirely for thousands of years would still not cover the energy cost of an interstellar journey. This relationship between mass, speed, and energy shows that nature imposes a practical barrier to relativistic motion. It is not merely a theoretical limitation, it is a matter of energy balance. The universe simply does not allow large masses to reach speeds close to light without destroying the very structure of motion itself. Therefore, the energy cost is not just an engineering difficulty, it is a physical impossibility. The energy required to move any object of considerable mass to a relevant fraction of the speed of light is so immense that it makes the project self-destructive. And it is this same law that keeps the cosmos in balance. The universe protects itself from its own disintegration by preventing matter from reaching absolute speed. Nothing travels faster than light, because the cost of doing so would be infinite. And infinity within physics is not a number, it is the boundary where everything ceases to exist. Even if humanity were to achieve total mastery of energy, propulsion, and space engineering, crossing the Milky Way would still be a task requiring millions of years. This is not a pessimistic estimate, but a direct physical calculation based on the dimensions of the galaxy and the limits imposed by relativity. The Milky Way is approximately 100,000 light-years in diameter. The Sun is located about 27,000 light-years from the center, which means that the nearest edge is still 70,000 light-years away. Even at the speed of light, the maximum possible limit, such a journey would take 70,000 years, but the central point is that no spacecraft with mass can travel at the speed of light. Even a modest fraction of that speed demands unimaginable energy. If we consider a theoretical spacecraft capable of reaching 10% of the speed of light, the travel time would increase tenfold. The journey to the galactic edge would take about 700,000 years. If the speed were reduced to only 1% of light, something closer to what could theoretically be achieved with nuclear or laser propulsion, the voyage would extend to 7 million years. And all this assumes the ship maintained a constant velocity, with no deceleration, technical failures, or collisions with interstellar particles. These numbers show that the problem is not only one of energy, but also of time. No known civilization, not even ours, possesses historical continuity long enough to sustain a project lasting millions of years. Human writing has existed for just over 5,000 years. Civilizations form, flourish, and vanish in periods short compared to the time needed to cross the galaxy. Any such mission would face the challenge of surviving not only technically, but also socially and culturally. Even the boldest proposals of theoretical physics, such as the warp drive or wormhole shortcuts, remain beyond the realm of feasibility. The warp drive, a concept derived from the Alcubierre metric, would require the manipulation of negative energy, something that has never been observed or created in a laboratory. Wormholes, though mathematically possible in the equations of general relativity, are unstable. They would collapse instantly under the slightest disturbance, demanding quantities of energy and quantum conditions that the observable universe simply does not provide. Even assuming that an advanced civilization could build a self-sufficient spacecraft capable of operating for millions of years, the limits of entropy would still prevail. Mechanical systems degrade over time, materials wear down, energy sources are depleted. Cosmic radiation would slowly damage the circuits and the biology of any living form. Even an automated probe would eventually lose functionality over the course of ages. The very notion of travel would become irrelevant in the face of such long-term deterioration. Nature also imposes additional obstacles. Interstellar space is not completely empty. It contains dust particles, hydrogen atoms, and high-energy radiation. At high speeds, each impact with a particle would release enough energy to pierce shields and destroy sensitive components. Over long periods, the spacecraft would face a continuous and inevitable bombardment, becoming a victim of the very medium it travels through. Even in ideal models, in which the ship could endure indefinitely and maintain energy stability, relativistic time dilation would not solve the problem. For the crew, the journey would seem shorter, as time inside the ship would pass more slowly. But for the external universe, millions of years would still go by. The civilization that launched the ship would cease to exist long before it arrived at its destination. Time would become a barrier more absolute than space itself. For comparison, the Voyager probes, launched by humanity at the end of the 20th century, are traveling at about 17 kilometers per second, which is less than 0.0006% of the speed of light. Even so, they would take more than 2 billion years to cross the galaxy if they maintained that speed. That number represents the difference between human scale and galactic scale, a gulf that no form of technical progress seems capable of bridging. Even advanced concepts such as Breakthrough Starshot, which proposes miniature probes propelled by lasers to reach 20% of the speed of light, face fatal problems. A spacecraft moving at such a fraction of light speed would be destroyed by impacts with tiny interstellar particles. Moreover, the energy required to maintain its course, correct its trajectory, and eventually decelerate would exceed all the solar energy collected by Earth over many years. For these reasons, the time required to leave the Milky Way is not just a matter of patience, it is a structural limit. The distance is so vast, and the achievable velocities are so small in comparison, that the result is inevitable. Even with the best conceivable technology, it would take humans millions of years to traverse the space between the Sun and the galactic edges. The universe is too vast to be crossed, and this is not a failure of science but a natural consequence of its laws. Light sets the rhythm of the cosmos, energy defines the cost of motion, and time, immutable, ensures that everything that exists remains within its proper scale. Even if humanity learns to master the atom, gravity, and space itself, it will still be limited by the very structure of the universe that created it. Traveling across the galaxy is possible only in thought. In practice, space and time conspire to keep us where we are. The Milky Way is an ocean so immense that even light does not cross it quickly. And while time flows, we remain trapped on a small point within this sea, observing, studying, and understanding, but never departing. At the heart of the Milky Way lies an invisible and silent force that holds the entire galactic structure together. The supermassive black hole, Sagittarius A star. Located approximately 27,000 light-years from Earth, in the center of the constellation Sagittarius, it is one of the most extreme objects known to science. Its mass is estimated to be about 4 million times that of the Sun, compressed into a region smaller than 40 solar radii. This inconceivable density creates a gravitational field so intense that nothing, not even light, can escape its pull within the so-called event horizon. Despite its reputation as a destroyer, Sagittarius A star neither devours the galaxy nor threatens the stars orbiting around it. On the contrary, it is one of the pillars that sustain the Milky Way's gravitational balance. Its presence provides a stable center of mass around which billions of stars revolve. Without such a massive central nucleus, the galaxy would lose cohesion over time, and its stars would scatter into interstellar space. The gravity of a star, combined with that of the entire stellar disk and the dark matter halo, is what keeps galactic rotation in equilibrium. The black hole is surrounded by an extremely active region known as the accretion disk. This is a ring of gas and dust spinning at near light speeds before being swallowed by the core. Friction and compression within this disk generate enormous heat, emitting radiation across multiple wavelengths, particularly in X-rays and infrared. It was through this radiation that astronomers were able to identify and study a star. In 2022, the Event Horizon Telescope captured the first indirect image of its outline, a luminous ring around a dark shadow, confirming its nature as a supermassive black hole. Near this center, space-time is warped in extreme ways. Stars orbiting a star follow elliptical paths at astonishing speeds, some exceeding 8,000 kilometers per second. Continuous observation of these stars, especially the so-called S2 star, was decisive in proving the existence of a compact, invisible object with millions of solar masses. This proof stands as one of modern astrophysics' greatest triumphs and confirms the predictions of general relativity. A star exerts an influence that extends far beyond its immediate neighborhood. Its gravitational field contributes to the overall motion of stars throughout the galactic disk. Although its mass represents only a tiny fraction of the Milky Way's total, about 1/10,000th, its central position makes it a gravitational axis. It is the point around which the entire galaxy rotates. Just as the Sun dominates the solar system, Sagittarius A dominates the Milky Way. There is also evidence that it was much more active in the past. Traces of ancient emissions suggest that the black hole once experienced intense accretion phases, releasing energy jets that stretched across tens of thousands of light years. Remnants of this past can be seen in the so-called Fermi bubbles, two enormous structures of radiation rising above and below the galactic plane. They indicate that Sagittarius A once fueled cosmic winds capable of influencing interstellar gas behavior and even the pace of new star formation. Even in its current calm phase, it continues to play a vital role in maintaining galactic stability. Without such a massive core, stellar orbits would become chaotic and disordered. Galactic rotation would lose symmetry, and the disk could fragment over billions of years. Instead of a well-defined spiral structure, the Milky Way would become a diffuse cloud of scattered stars. Sagittarius A, therefore, is not merely a cosmic curiosity. It is a structural element, a gravitational anchor that gives the Milky Way its shape and cohesion. Around it, the density of stars is so high that the sky would appear constantly bright if we were near the center. Thousands of stars orbit within a volume smaller than the distance between the Sun and its nearest neighbor. In this extreme environment, stellar collisions, supernovae, and violent magnetic fields are common. The galactic center is a natural laboratory for studying physics under conditions impossible to reproduce in any human experiment. The presence of a supermassive black hole at the core of galaxies is not unique to the Milky Way. Observations show that nearly all large galaxies possess a similar nucleus. This suggests that such objects play a fundamental role in the formation and evolution of cosmic structures. Without them, galaxies might not exist in the organized form we observe. The gravity concentrated in such a dense point seems to have been one of the ingredients that shaped the universe during its first billions of years. Sagittarius A is, therefore, both a boundary and a bond. It represents the extreme of gravity, where space and time merge into a single point, yet it is also the center that holds the entire galaxy together. To look at it is to glimpse the paradox of the cosmos, a force that destroys and, at the same time, sustains. The Milky Way exists only because its heart is an abyss. The Milky Way is not just a collection of stars spinning around an invisible core. It is a dynamic system, sustained by a web of gravitational forces balanced on a colossal scale. Every star, planet, gas cloud, and dust particle contributes its own fraction of gravity to the whole. The result is a collective field of attraction that keeps the galaxy cohesive and in motion. This interaction among billions of bodies is what gives the Milky Way its spiral shape and its stability over billions of years. Gravity is a weak force compared to the other fundamental forces of nature, but it is the only one that acts over long distances and is never cancelled out. While electrical and nuclear forces balance or neutralize each other, gravity only adds up. Every star attracts all the others, and this constant sum is what keeps the galaxy united. It is a cosmic dance in which all bodies are connected. The Sun, for example, does not orbit only the black hole Sagittarius A star, but also feels the combined pull of all the stars and matter that make up the galactic disk. This collective force is distributed so evenly that the resulting motion is stable and predictable. However, when astronomers began measuring the velocities of stars on the outer edges of the galaxy, something didn't make sense. According to known laws of gravitation, the farthest stars should rotate more slowly, just as the outer planets of the solar system move more slowly than the inner ones. But observations showed the opposite. Stars in the outer regions maintained almost the same speed as those closer to the center. This would only be possible if there were much more mass in the galaxy than we can see. Thus arose the concept of dark matter, an invisible form of matter that does not emit, reflect, or absorb light, but exerts gravity. The existence of this substance was deduced from its effects on the motion of stars and galaxies. Today, it is known that about 85% of the Milky Way's mass base is made up of dark matter. The remainder, all the stars, planets, gases, and dust, represents only a small fraction of the total. This invisible matter forms a gigantic structure called the dark matter halo, which surrounds the entire galaxy like a sphere. While the visible disk of the Milky Way measures about 100,000 light-years across, the halo may extend over 300,000 light-years in every direction. It is what keeps the outer stars in orbit, preventing them from escaping the galaxy's gravitational pull. Without the halo, the Milky Way would slowly disintegrate, losing its edges to intergalactic space. The nature of dark matter remains one of the greatest mysteries of modern physics. It does not interact with light or with common electromagnetic forces, making it invisible to traditional telescopes. Numerous experiments have tried to detect its particles, commonly called WIMPs, or weakly interacting massive particles, but so far none have been directly observed. Even so, the gravitational evidence is undeniable. The rotation curves of galaxies, the behavior of galactic clusters, and the bending of light in gravitational lensing phenomena all confirm its presence. In addition to maintaining the galaxy's structure, the dark matter halo also influences star formation. Its gravity shapes the collapse of gas clouds and determines where and how new stars can be born. The distribution of dark matter acts as an invisible skeleton upon which luminous matter organizes itself. Without it, the Milky Way would not have the spiral shape we know and might not even exist as a stable system. The collective gravitational force of the stars, combined with that of the dark halo, is what maintains the balance of galactic rotation. Each star, even when isolated, participates in this global system. When the sun moves, it responds not only to the pull of the center, but also to the sum of forces from trillions of bodies scattered throughout the disk. It is a precise choreography where the combined weight of the galaxy creates a continuous and deep gravitational field. For the human observer, this force is imperceptible, but on cosmic scales, it is what prevents the dispersion of the local universe. The Milky Way has been spinning for billions of years and will continue to do so for billions more, sustained by an invisible structure that never rests. Collective gravity is silent, patient, and eternal. Dark matter, though mysterious, is the glue of the cosmos. Without it, galaxies would not hold together, stars would not cluster, and the universe would be a diffuse cloud of scattered particles. It is evidence that what truly sustains reality is not what we see, but what we feel through gravity. The Milky Way is therefore a balance between the visible and the invisible. Its stars shine, but it is the dark halo that supports them. It is this combination that makes the galaxy exist, and it is also what keeps us bound to it. No human force can break a gravitational field born from the sum of billions of stars and a form of matter we do not yet know. Escape velocity is a simple yet essential concept for understanding the physical limits that keep everything bound to a celestial body. It represents the minimum speed required to overcome the gravitational pull of an object without needing any further propulsion. To escape Earth, a rocket must reach 11 kilometers per second. To escape the Sun, it must exceed 42 kilometers per second. But to escape the Milky Way, the required speed is about 500 to 600 kilometers per second, more than 1,000 times faster than any human spacecraft has ever achieved. That number, though it might seem like a distant abstraction, represents a practical absolute barrier. It defines the limit of what is physically possible within the galactic structure. The gravity of the Milky Way is the sum of the attraction of hundreds of billions of stars, of enormous clouds of gas, of the central black hole Sagittarius A, and of the dark matter halo that envelops everything. Escaping this combined force would require such immense energy that no known civilization could ever generate it. Even the fastest stars ever observed, the so-called hypervelocity stars, rarely reach this limit. Some of them are ejected from the galactic center after violent interactions with Sagittarius A. In these gravitational encounters, a star can be hurled at more than 1,000 kilometers per second, fast enough to escape the Milky Way. But such cases are exceptional and catastrophic. They do not escape by their own power, but rather through cosmic accident. They are products of extreme physics, not of controlled engineering. For any massive object, such as a spacecraft, the situation becomes even more complex. The energy required to reach 500 kilometers per second increases in proportion to its mass and the efficiency of its propulsion system. Even the most ambitious technologies conceived by theoretical physics, fusion engines, antimatter drives, or laser propulsion, come nowhere near that threshold. The energy demanded would equal the complete conversion of large quantities of matter into pure energy, something impossible without violating fundamental laws. Beyond the energy problem, there is the issue of the galaxy's non-uniform gravitational field. The Milky Way is not a homogeneous sphere, but a flattened disk with regions of variable density. This means the escape velocity changes depending on location. Near the center, it is even greater, potentially exceeding 900 kilometers per second. On the edges, it decreases, but never enough to make escape possible with any known technology. Escape velocity is also not a point of arrival. Even if a spacecraft managed to reach that speed, it would need to maintain it continuously, resisting the opposing forces of gravity and interactions with the interstellar medium. Tiny energy losses over millions of years of travel would be enough to slow it down and pull it back. The space between galaxies is a field of potential energy in unstable equilibrium, and maintaining a trajectory of escape is like trying to keep an arrow flying forever through the void. To understand the scale of this limit, it helps to compare it with natural phenomena. The plasma jets emitted by active black holes, colossal structures releasing energy equivalent to billions of suns, reach significant fractions of the speed of light, yet remain trapped within the gravitational field of their host galaxies. If even the most powerful forces in the universe cannot escape easily, it is evident that no ship built by any material civilization ever could. Another determining factor is the role of the dark matter halo. It extends the gravitational influence of the galaxy far beyond its visible region. This means that even after crossing the luminous boundary of the Milky Way, the point where stars grow sparse, a spacecraft would still be within its invisible gravitational field. The true limit of the galaxy is not what we see but what we feel through gravity. To escape completely, one would have to overcome the pull of the halo, which stretches for hundreds of thousands of light years. The galactic escape velocity, therefore, is not just a theoretical figure. It is the numerical translation of a cosmic boundary. It defines the maximum reach of any body that still belongs to the Milky Way. Anything below that speed will remain forever bound to the galaxy, orbiting it in some form, even if along eccentric and distant trajectories. This impossibility of escape is also what gives the cosmos its stability. If escaping were easy, galaxies would disperse rapidly, and the universe would become an empty, uniform space. The balance between gravitational force and kinetic energy is what sustains cosmic structure. Escape velocity is not an imposed prison, but a consequence of the harmony of forces. Thus, even if humanity one day masters the energy of the stars and reaches speeds near that of light, it will still remain trapped within the same gravitational field that shaped its origin. The Milky Way is a system closed by its own nature. Everything born within it remains part of it. Because its gravity is more than a force, it is the physical expression of the bond between matter and space. Escaping the Milky Way is not just a matter of power. It is a challenge against the very design of the universe. Galactic escape velocity is a reminder that, no matter how far we may travel, we will still be within the same field of force that created us. Escaping Earth, the solar system, and the galaxy, are three completely different levels of gravitational liberation, each more difficult and more energy demanding than the previous one. These three thresholds clearly illustrate the gulf between what human beings are capable of doing and what the universe requires to be overcome. At each scale, the energy required increases in proportions that defy any imagination. Earth is the first step of this cosmic hierarchy. Its gravity is strong enough to keep everything we know, oceans, atmosphere, and even the moon, bound to its surface. To escape this force, an object must reach the so-called terrestrial escape velocity of approximately 11.2 kilometers per second. That equals about 40,000 kilometers per hour. Modern rockets reach this value only for instance, using enormous amounts of fuel and ingenious staging sequences to reduce weight and increase thrust. Even so, escaping Earth does not mean escaping the Sun. Upon leaving the planet, a vehicle merely enters solar orbit, remaining a prisoner of the star. To escape the Count solar system, and the task is far more complex. The Sun exerts a gravity incomparably greater than Earth's, and to overcome it one must exceed the Higgs solar escape velocity, which depends on the point of departure. From Earth's orbit, this value is about 42 kilometers per second. This means that any spacecraft launched from here must gain enough energy not only to escape Earth's pull, but also to free itself from the Sun's gravitational field. To date, very few human-made objects have achieved this. The Voyager 1 and 2 Suns, Pioneer 10 and 11, and New Horizons probes are the only ones to reach the speed required to leave the solar system. Even so, they are still in its immediate neighborhood, and their speeds are negligible in galactic terms, less than 0.0006% of the speed of light. Now, when we widen this scale to the Milky Way, the challenge becomes immeasurable. The galaxy is not a compact body like a planet or a star, but a gigantic system composed of hundreds of billions of masses mutually interacting. Its gravity is the result of the sum of all these combined forces, including dark matter, which forms the galactic halo. The galactic escape velocity, measured from the Sun's position, is about 500 to 600 kilometers per second. This value is more than 10 times greater than the speed of any human probe and 50 times greater than the solar escape velocity. This comparison reveals an almost incomprehensible scale. Escaping Earth is a feat of engineering. Escaping the Sun is an achievement of civilization. Escaping the galaxy is, as far as we know, physically impossible. The difference among them is not only one of energy, but of order of magnitude. The energy required to leave the Milky Way is so many times greater than what is available that even by converting an entire planet's mass into fuel, it would not be enough. Another important factor is the time involved. Leaving Earth takes minutes. Leaving the solar system takes decades. Leaving the galaxy would take millions of years, even at speeds close to that of light. Each scale adds not only distance but duration. The galactic vastness is so great that time itself becomes an obstacle. The difference among these three levels also lies in the nature of the environment. Space around Earth is relatively protected. Space between planets is cold but predictable. Interstellar and galactic space, however, is completely hostile. Cosmic radiation is intense. Energetic particles move in all directions, and the distances are so immense that no kind of resupply would be possible. Even a self-sufficient spacecraft would face irreversible degradation before traversing a fraction of the galaxy. In gravitational terms, each step is a prison inside another prison. Earth keeps humanity on its surface. The Sun keeps Earth in its orbit, and the Milky Way keeps the Sun within its disk. Escaping one does not mean escaping the next. Even if humans one day manage to live beyond the solar system, they will still be completely bound to the galaxy that contains them. Cosmic freedom, therefore, is relative. We may leave planets and stars, but we will never leave the structure that houses them. This gravitational hierarchy is what gives the universe its stability. Without it, orbits would collapse, and the cosmos would be chaos. The same force that prevents us from escaping is the one that keeps everything in place. Gravity is at once the prison and the foundation of existence. Escaping Earth is conquering engineering. Escaping the Sun is conquering energy. Escaping the galaxy would be conquering the very laws of the universe. and no civilization, however advanced, can exist outside those laws. They are the invisible fabric that sustains time, space, and life. The Sun, which appears to be the unchanging center of our solar system, is in fact a traveler, trapped in a colossal orbit around the core of the Milky Way. Just as Earth revolves around the Sun and all its planets revolve around the galactic center, a region dominated by the supermassive black hole Sagittarius, a star, and by the combined weight of billions of stars and the dark matter surrounding them. This orbit is the invisible prison that defines the solar system's position within the cosmos. The Sun's path around the galaxy is immense and slow. It moves at an average speed of 220 kilometers per second, completing a full revolution around the galactic center every 230 million years. That means that since Earth's birth, the Sun has completed only about 20 full revolutions around the Milky Way. Each galactic rotation is called a cosmic year, and the entire geological and biological record of Earth, from the dinosaurs to the emergence of humanity, has taken place within only a tiny fraction of that journey. This orbit is not perfectly circular. It resembles a gentle ellipse, and the Sun also oscillates up and down relative to the galactic plane, moving in a kind of wave as it advances. These oscillations cause the solar system to pass through denser and more diffuse regions of the galaxy at intervals of tens of millions of years. Each passage through these zones may have subtle but profound effects on Earth's cosmic environment, altering radiation flux, comet bombardment, and possibly even the pace of biological evolution. The gravitational field that keeps the Sun in its orbit is the sum of all the forces within the Milky Way. The combined mass of stars, gases, dust, and dark matter generates an attraction that holds it firmly in place. No propulsion could ever break this bond. Even if the Sun somehow received a colossal push, its kinetic energy would have to be sufficient to overcome the gravity of the entire galaxy, an impulse equivalent to the release of energy from millions of supernovas, something nature does not offer and technology could never reproduce. The planets orbiting the Sun share the same fate. They do not orbit only the star, they orbit the galaxy along with it. The entire solar system is a closed gravitational set, moving as a single unit. Every second, Earth travels thousands of kilometers through space around the galactic center, dragged by the force that holds the Sun captive. Humanity lives within a system in perpetual motion, yet that motion is circular, a prison without walls, from which there is no escape. What is most fascinating is that this prison is imperceptible. No observer on Earth feels the galaxy's gravity directly. What we sense is only the planet's local gravity, but it is the combined force of the Milky Way that defines the limits of our existence. The Sun cannot escape, and therefore nothing orbiting the Sun can. This dependence creates an absolute gravitational hierarchy. The planets are bound to the Sun is bound to the galaxy, and the galaxy is bound to the cosmic web of the universe. This relationship is also dynamic. The Sun does not travel alone. It is accompanied by millions of neighboring stars following similar paths, forming a vast stellar flow. Together, these stars make up the galactic disk, a constantly rotating structure maintained by a balance between centrifugal force and gravity. If that balance were ever disturbed, the galaxy would slowly disintegrate. It is this harmony between motion and attraction that keeps the cosmos organized. Throughout its journey, the Sun passes through different regions of the galaxy: spiral arms, stellar nurseries, clouds of gas and dust, and zones of intense radiation. Each of these areas has its own characteristics, and passage through them can alter the flux of comets or increase Earth's exposure to cosmic radiation. Some studies suggest a possible correlation between the solar system's passage through certain galactic regions and mass extinction events on Earth. Although these correlations remain debated, they illustrate how deeply the fate of terrestrial life is intertwined with the Sun's movement through the Milky Way. Even the most distant bodies of the solar system, such as the Oort cloud, a vast reservoir of comets extending trillions of kilometers, remain under the influence of the galaxy. This cloud marks the outer boundary of the Sun's gravitational dominion, yet it still bends in obedience to galactic gravity. The Sun is only a link in a far greater chain, and its freedom ends where the Milky Way's gravity begins. This reality turns the solar system into a kind of captive microcosm. Everything we know, Earth, the planets, the asteroids, and even sunlight itself, is part of a system in perpetual orbit. The illusion of isolation we experience is only a consequence of scale. Every second, while we orbit the Sun, we are also orbiting something far greater. The Sun is a prisoner, yet it is also sustained by that imprisonment. If it were free, it would drift through interstellar space until it was captured by another gravitational field, perhaps destroyed in a collision with another system. The gravity that confines it is also the force that protects it. The Milky Way not only contains the Sun, it defines it. Humanity, therefore, does not live on an isolated planet, nor within an independent system. We live inside a cosmic organism in constant motion. The Sun and its planets are but cells within that greater body. Escaping it is not a matter of technology, but of nature. What holds us captive is not a physical barrier, but the very fabric of the universe. When viewed edge-on, the Milky Way reveals an extraordinarily thin and extensive structure, a rotating disk composed of hundreds of billions of stars, gas clouds, interstellar dust, and vast bands of invisible dark matter. This disk, about 100,000 light-years in diameter, and only 1,000 light-years in average thickness, is the dynamic heart of the galaxy. It is where most stars are located, including the Sun, and it is there that the collective orbital motion keeps the galaxy bound and in balance. Each star in the disk follows its own orbit around the galactic nucleus, yet all move within a general pattern of rotation. The orbital speed of the stars depends on their distance from the center. In the innermost regions, gravity is intense and the stars spin faster. At the outer edges, where visible mass diminishes, motion should theoretically slow down. However, observations show that stars at the edges maintain almost the same speed as those in the interior, one of the most direct pieces of evidence for the MAOS dark matter halo, whose invisible gravity sustains the uniform rotation of the disk. The galactic disk is divided into two main layers, the thin disk and the thick disk. The thin disk contains most of the young stars, gas and dust, regions where star formation is still taking place. The thick disk, by contrast, is made up of older, more yellowish stars with a lower concentration of heavy elements. This distinction reflects the Milky Way's evolutionary history. The thick disk represents an older, more turbulent phase of the galaxy, whereas the thin disk is the product of billions of years of stabilization. Stars do not move in perfectly flat trajectories. They oscillate up and down relative to the galaxy's midplane, describing a wave-like motion as they complete their orbits. This behavior creates a three-dimensional pattern that gives the disk a slight curvature. The Sun, for example, undergoes one of these oscillations every 60 to 70 million years, rising and falling by tens of light-years relative to the galactic plane. This oscillation carries it through regions of varying density, influencing the cosmic environment and potentially Earth's own geological history. The rotation of the disk is stable, but not rigid. The Milky Way rotates so differentially, which means the inner parts complete a revolution in less time than the outer parts. This difference makes our spiral arms, those luminous bands that define the galaxy's shape, not fixed structures, but density waves that travel through the disk. As gas and stars enter these denser regions, they are compressed, triggering the birth of new stars. That is why the spiral arms shine more brightly. They are zones of active star formation marked by young, hot, bluish stars. The collective motion of stars within the disk is a direct manifestation of gravity on a large scale. No single body dominates the motion. What keeps the system together is the sum of all masses. Each star, however small, contributes a fraction of that force. In this sense, the Milky Way is a living gravitational organism, in constant balance between attraction and motion. This stability, however, is not eternal. Over billions of years, interactions with satellite galaxies and the disk's own motion through the dark halo gradually alter its properties, generating ripples, warps, and subtle asymmetries that astronomers are mapping with increasing precision. Stellar orbits within the disk are almost circular, but they display small variations caused by gravitational perturbations, close encounters with other stars, giant molecular clouds, or high-density regions. These interactions cause stars to slowly migrate from one orbit to another over millions of years. The Sun, for example, may not have formed exactly where it is today. Evidence indicates it was born closer to the galactic center and gradually drifted outward in a process known as radial migration. Another fascinating aspect is that the galactic disk is not completely flat. It shows a slight S-shaped deformation, known as the line to galactic warp plan, observable at the outer edges. This curvature results from gravitational interactions with smaller neighboring galaxies, such as the Magellanic Clouds, and from the influence of the dark matter halo. This deformation shows that the Milky Way is a flexible system, sensitive to external forces, and one that continues to evolve. To understand the disk's behavior, astronomers use enormous data sets generated by space missions such as Gaia, which maps the positions and velocities of billions of stars with unprecedented precision. These studies have revealed that the disk is not a static structure, but an ocean in motion, full of waves, eddies, and gravitational streams. Each star is like a drop in this cosmic sea, contributing to the global flow while never escaping its current. The galactic disk is therefore the broadest and quietest gravitational prison that exists. The stars that inhabit it, including the Sun, are forever trapped in their orbits, moving along paths that last hundreds of millions of years. There is no possible escape, only perpetual motion. The Milky Way spins but never comes apart. It is the ultimate example of harmony between force and balance, a system so vast that it contains within itself the destiny of all the worlds it hosts. Thus, when we look at the sky and see the luminous band of the galaxy stretching across the night, what we are seeing is the very disk to which we belong, the gravitational field that envelops and defines us. Every point of light is a prisoner, spinning endlessly around an invisible nucleus, within a structure that never repeats and never falls apart. The classic image of the Milky Way with its majestic spiral arms is not merely a visual structure. It is a direct consequence of the gravitational dynamics that govern the galaxy. The stars, including the Sun, do not rotate in perfect circles around the core. Their trajectories follow a spiral pattern, moving slowly through the galactic arms and crossing regions of varying density over millions of years. This movement results from a delicate balance between gravity, angular momentum, and the density waves that sweep through the galactic disk like cosmic tides. The spiral arms are not always made up of the same stars. They are not fixed objects, but gravitational waves that travel through the disk, compressing gas and dust as they move forward. This compression creates new regions of star formation. When a star is born inside an arm, it eventually leaves it behind, continuing its orbit around the galactic center. The arm, however, continues to exist, sustained by the constant passage of new stars and interstellar clouds. This is the basis of what astronomers call the density wave theory, proposed in the 1960s and widely confirmed by modern observations. The Sun is one of those stars that cross the galactic arms at regular intervals. It completes one revolution around the galaxy every 230 million years, but the spiral arms move at a different angular velocity. This causes the solar system to pass through these bright regions roughly every 100 million years. In each crossing, the cosmic environment around it changes. The increased density of gas and dust can intensify the bombardment of comets coming from the Oort cloud, and stellar radiation can become more intense. Some studies suggest that these crossings coincide in certain cases with mass extinction events on Earth, possibly through the indirect influence of the galactic environment. The spiral trajectories of the stars are not rigid, but the result of a set of forces that interact subtly. The combined gravitational field of the entire galaxy creates a potential that curves and distorts, guiding the stars along paths resembling logarithmic spirals, the same type of curve found in shells, cyclones, and distant galaxies. This similarity is not a coincidence. It is a natural form of dynamic equilibrium. In a rotating system with variations in speed and density, the spiral is the structure that spontaneously arises to maintain harmony between motion and gravity. The Sun does not follow a single continuous spiral, but a sequence of slightly eccentric orbits that cause it to migrate slowly within the galactic disk. This process, known as radial migration, is caused by gravitational interactions with giant molecular clouds and with the density arms themselves. Over billions of years, the Sun may have shifted thousands of light years from its original birthplace, approaching and moving away from the galactic center in slow, imperceptible cycles. This migration is common to all stars in the disk and is one of the factors that mix stellar populations, balancing the galaxy's chemical composition. The spiral trajectories also explain why the Milky Way maintains its cohesive shape. Differential rotation, in which the inner parts rotate faster than the outer ones, should, over time, distort the galaxy, stretching and unraveling its arms. However, the density waves act as gravitational molds that reorganize the disk's material, preserving the spiral design. The galaxy rotates, yet its patterns remain, like a cosmic melody repeating in an endless cycle. To visualize this motion, imagine a sheet of water swirling in a whirlpool. The particles do not follow fixed lines. They approach and move away from the center, tracing curved paths that converge into invisible spirals. The Milky Way works the same way, only on an incomparably larger scale. Each star is a drop of light in this gravitational flow. The Sun is one of them, a particle of fire in an ocean of continuous movement. Observations from satellites such as Gaia have confirmed that the Milky Way's disk is not static. Gravitational waves, external disturbances, and interactions with smaller galaxies generate vertical oscillations and density variations that alter stellar trajectories. On a large scale, this causes the entire disk to pulse slowly, as if it were breathing. This pulsation is imperceptible on human timescales, but over billions of years, it shapes the structure and destiny of the galaxy. With each revolution the Sun completes, it passes through different regions, star-forming zones, fields of dark dust, and emptier areas between the arms. These passages are like chapters of a journey that never ends. And even though it seems free, the Sun is always following a path drawn by the collective gravity of the Milky Way. It does not choose its way. It simply fulfills it, obeying the laws of space-time. The spiral trajectory is therefore the symbol of gravity's gentle prison. The stars are not bound by chains, but by geometries. They move freely, yet only within the limits imposed by the galactic field. This controlled freedom is what makes the galaxy stable and eternal. Thus the Sun and all the other stars follow their silent spirals, moving at a rhythm that lasts hundreds of millions of years. None of them will ever leave the Milky Way. They are born, spin, and die within it, following a curve that repeats infinitely in the fabric of the cosmos. The universe is in constant motion, but that motion is not absolute. Everything that moves does so relative to something else, and it is this relativity that gives the cosmos its structure and complexity. Within the Milky Way, the stars, gas, and dust revolve around the galactic center, but they do not spin like a solid wheel. They move at different speeds, depending on their distance from the core, creating what astronomers call differential rotation, a phenomenon that defines the dynamic behavior of spiral galaxies and explains why they maintain their shape for billions of years. Differential rotation means that the inner regions of the galaxy rotate faster than the outer ones. Near the core, the mass density is higher and gravity is stronger, causing stars to complete their orbits in less time. In the more distant regions, where visible mass is lower, stars should theoretically rotate more slowly, yet observations show that they do not. Their speeds remain nearly constant throughout the disk. This anomalous behavior is only possible because of the influence of the dark matter halo, whose invisible gravity stabilizes the motion, preventing the outer parts from dispersing. To grasp the magnitude of this phenomenon, one must imagine the galaxy as a gigantic whirlpool of stars. Each star, each cloud, and each grain of dust follows its own path, influenced by the sum of all surrounding gravitational forces. There is no fixed or stable point. There is no immobile center. Everything is in motion, even the space between objects. The Sun, for example, completes one revolution around the galactic core every 230 million years. But in that same time span, the inner regions have completed several orbits, while the outer ones have barely moved. This difference in speed creates a continuous twist in the disk, a dynamic flow that gives rise to the spiral arms. This motion is not only physical, but perceptual. The concept of absolute movement does not exist in modern physics. Since the theory of relativity, it has been understood that there is no fixed point of reference in the universe. Everything moves in relation to something else. To an observer on Earth, the Sun appears to cross the sky. To an observer outside the galaxy, the Sun is just another star trapped in an invisible orbit. And to an observer beyond the visible universe, Both would be part of an even larger system in continuous expansion. This absence of absolute reference turns motion into an illusion dependent on perspective. Differential rotation is the mechanism that makes galaxies alive. Without it, spiral disks would have no defined form and would slowly dissipate into space. It creates the perfect tension between gravitational collapse and centrifugal dispersion, maintaining the dynamic equilibrium that allows stable structures to exist. It is a motion that never ends, yet never repeats exactly. Each star as it moves draws a unique trajectory through space-time, different from all others. This difference in speeds also has subtle effects on the internal structure of the galaxy. Over time, the faster regions drag the slower ones, generating waves of density that propagate through the disk as luminous spirals. These waves concentrate gas and dust, triggering the birth of new stars. Thus, differential rotation is not merely a mechanical effect. It is a creative cycle, a process that keeps the galaxy in constant renewal. What is most fascinating is that for observers within this system, like us, everything seems still. Galactic motion is so vast and so slow on a human scale that it escapes direct perception. We live inside a whirlpool of stars, but to us, it is invisible. The constellations appear fixed, the heavens seem static, and the universe gives the illusion of stability. That illusion is simply the result of scale. Human time is an insignificant fraction of cosmic time. The idea of absolute movement collapses completely in this scenario. Even if a spacecraft were to travel at near light speed, it would still be trapped in the motion of the galaxy. All it could do would be to change its relative position within a rotating system. No point in the universe is truly motionless. Even entire galaxies move within clusters, drawn by other galaxies and by the large-scale structure of the cosmos. This reality turns the notion of displacement into something philosophical. To move in the universe is like moving within a river. It is impossible to stand still, but it is also impossible to escape the current. Differential rotation is the current of the Milky Way, a constant, gentle, and inevitable force. In the end, absolute motion is an illusion, and differential rotation is the reminder of it. Each star spins at its own rhythm, yet all are bound by the same invisible gravity. The universe moves on scales the human mind can barely conceive, and what we call rest is merely motion too slow to be seen. The Milky Way has been rotating for billions of years and will continue to do so for billions more. No star will ever stop. Differential rotation is the heartbeat of the galaxy, the silent sound of gravity in balance with time. The center of the Milky Way is a region where the familiar laws of physics still apply, but at their most extreme limits. It is an environment so dense, energetic, and chaotic that no civilization, no matter how advanced, could inhabit it or even approach it safely. It is the gravitational heart of the galaxy, but also its cosmic inferno, a place where space and time bend under colossal forces. At the galactic nucleus lies the supermassive black hole Sagittarius A, containing about 4 million times the mass of the Sun. Surrounded by a disk of gas and dust, heated to millions of degrees. Around it orbit stars at absurd speeds, some reaching 8,000 kilometers per second. These so-called galactic center stars are the fastest known in the universe, and their distorted trajectories reveal the immeasurable power of gravity in that region. Any object that ventures too close would be torn apart by the difference in gravitational force between its parts, a phenomenon known as spaghettification. The galactic center is also one of the most hostile regions of the universe in terms of radiation. The accretion disk surrounding Sagittarius A emits intense X-rays, ultraviolet radiation, and jets of relativistic particles. These energy flows are capable of destroying molecules, ionizing gases, and sterilizing any form of life. Even at a safe distance of dozens of light years, exposure to such energy levels would be lethal to both biological organisms and electronic systems. Beyond radiation, the stellar density in that region is so high that gravitational collisions are constant risks. Within a radius of only a few light years around the nucleus, there are millions of stars, many of them massive and unstable. Their supernova explosions are frequent and release amounts of energy equivalent to billions of nuclear bombs. The sky there would never be dark. It would be a storm of lights, explosions, and violent magnetic fields. No material structure could survive in such an extreme environment. The Taos magnetic field at the galactic center is another factor that makes it uninhabitable. It is hundreds of times stronger than the average magnetic field of the galactic disk, and its complex interaction with ionized gas creates streams of high-energy particles that extend for thousands of light years. These currents distort any attempt at navigation or communication. A hypothetical civilization approaching the nucleus would face total communication failure, instrument malfunctions, and the gradual destruction of its structures due to radiation and tidal forces. The giant molecular clouds surrounding the core are equally lethal. These are dense masses of gas and interstellar dust that can collapse under their own gravity to form new stars, but they are also regions of intense turbulence and compression. The density of these clouds is so great that any spacecraft, even with advanced shielding, would be engulfed and destroyed by friction with plasma and uneven gravitational pressure. The galactic center is, in essence, a zone of destruction and rebirth. It is where matter falls into the black hole and disappears, but also where new stars are born from the cosmic ashes. This duality makes it the engine of the galaxy, an endless cycle of creation and annihilation. Yet for any form of intelligent life, it remains a forbidden frontier. No biology or technology could survive where the very fabric of space is distorted every instant. Even on larger scales, the consequences of approaching the core would be fatal. Gravitational forces could strip planets of their atmospheres, disintegrate rocky bodies, and deform any solid object. Space-time there is so warped that the notion of direction loses all meaning. What we call up and down, inside and outside, cease to exist. Civilizations, if they exist elsewhere in the galaxy, instinctively know, or have learned through observation, that the center is a place to be avoided. Even forms of life capable of surviving in extreme cosmic conditions would find no stability in an environment where everything changes every second. Nature there is pure collapsing energy, and physics dissolves into chaos. From a scientific perspective, the galactic center is the boundary of observation and understanding. The laws of relativity and quantum mechanics intertwine in ways still not understood, creating conditions where time slows down and information is lost forever beyond the event horizon. No data, no message, no signal escapes from there. That is why the center of the Milky Way is a forbidden region. Not by external decree, but by physical impossibility. It is the heart of the galaxy, but also its abyss. Everything that comes too close is destroyed, and everything that moves away remains forever bound by its gravity. The center is the clearest symbol of humanity's cosmic condition. We orbit the mystery, but never touch it. The Milky Way is a prison of beauty and destruction, and its core is the central cell. No being, no ship, no civilization can exist where space and time dissolve. The center of the galaxy is the point where the universe reveals its maximum power and reminds all that there are places where existence itself is simply not possible. Traveling to the center of the Milky Way is, from any physical point of view, an impossibility. The distance, the energy required, the forces involved, and the environmental conditions make the galactic nucleus an insurmountable frontier for any form of navigation, whether biological or technological. It is not an engineering limitation, but an impossibility imposed by the very fundamental laws of the universe. The galactic center is located approximately 27,000 light-years from Earth. This means that light, the fastest thing in the cosmos, takes 27,000 years to get there. If a spacecraft traveled at the speed of light, it would take the same time to cover that distance. But since no object with mass can reach that speed, any attempt at a journey would take at minimum hundreds of thousands of years, even with theoretical technologies far beyond our current understanding. The first obstacle would be the energy needed to accelerate a spacecraft to significant fractions of the speed of light. As we have seen previously, energy grows exponentially as speed increases. Getting a craft of a few tons to 1/10 the speed of light would require more energy than humanity has produced in its entire history. And that would only be for acceleration. The same amount of energy would be needed to brake upon arrival, doubling the energy cost. The second obstacle is the interstellar medium. The space between the stars, although it seems empty, contains particles of gas and dust. At relativistic speeds, even a hydrogen atom becomes a deadly bullet. A tiny particle striking a craft at that speed would release energy comparable to an artillery explosion. The constant impact of these particles would destroy any material structure before the craft completed even a fraction of the journey. In addition, there is the problem of cosmic radiation. The path to the center of the galaxy passes through regions of intense ionizing radiation, especially near the nucleus. The constant bombardment of highly energetic particles would damage electronic circuits, destroy shielding, and make any kind of biological crew unviable. Even with perfect shields, the energy accumulated over millions of years of travel would ultimately be lethal. Navigation would also be impossible. As the craft approached the center, the gravitational field would become increasingly complex and unpredictable. The presence of massive stars, secondary black holes, collapsing gas clouds, and shock waves would create a constantly changing gravitational maze. No guidance system could operate stably in such an environment. Space-time would be distorted so extremely that even the notion of a trajectory would cease to make sense. And even if, hypothetically, a craft could survive all this and reach the nucleus, it would face the final limit, the supermassive black hole, Sagittarius A star. The region around it is dominated by gravitational fields so intense that the difference in force between the front and back of any object would destroy it instantly. No known material would withstand the extreme deformation caused by differential gravity, the phenomenon of spaghettification. Moreover, the accretion disk around the black hole is a cosmic furnace with temperatures of millions of degrees and radiation sufficient to vaporize any solid matter. Another critical factor is time. Even if the crew were protected and managed to travel at speeds close to that of light, time inside the craft would pass more slowly due to relativistic time dilation. For those on board, the journey might seem to last a few decades, but for the external universe and for any observer on Earth, tens of thousands of years would have passed. Upon returning, the civilization that sent them would already have disappeared, and perhaps even the sun itself would no longer exist. The effects of extreme gravity would also alter the very structure of space-time. Near the nucleus, the curvature of space would be so intense that the craft would follow trajectories inevitably curved toward the black hole, with no possibility of maneuver. Even if it tried to brake, the energy required to escape again would be greater than all the energy contained in the mass of the craft itself. Finally, there is the limitation of perception. As it approached the center, time for the external observer would begin to slow. Seen from Earth, the craft would appear never to reach the black hole, only to move more and more slowly, freezing in space. For the crew, however, the passage of time would continue normally until the moment of collapse. The journey would end not with arrival, but with the dissolution of perceived reality itself. These barriers make the galactic center not only inaccessible, but in principle uninhabitable. It is a region of forces so intense that they exceed the physical limits of any form of organized matter. No shield, energy field, or future technology could turn this environment into something habitable. The core of the galaxy is the domain of pure gravity, a place where the universe reveals its absolute power, and where the very concept of travel ceases to make sense. For this reason, even the most advanced imaginable civilizations would remain far from the galactic center. Not out of fear, but because nature makes it forbidden. The center of the Milky Way is not a destination. It is a boundary. It is the point where every journey ends, and where space and time curve until they vanish. The nucleus of the Milky Way is one of the most violent and energetically active places in the universe. Unlike the calm regions where the sun resides, the galactic center is dominated by destructive forces that constantly reshape the environment. Among these forces, two stand out for their intensity and impact: supernovas and stellar winds. Together they transform the core into a furnace of energy, turbulence, and radiation, making it a forbidden environment for any form of life, and a challenge even for matter at rest. Supernovas are stellar explosions that occur when massive stars reach the end of their lives. In the galactic center, where the stellar density is extremely high, these explosions occur much more frequently than in the outer regions of the galaxy. It is estimated that, in the heart of the Milky Way, a supernova happens on average once per century, a cadence sufficient to keep space permanently agitated. Each one releases in just a few seconds an amount of energy equivalent to what the Sun will emit over its entire lifetime. When a supernova explodes, it sends shock waves sweeping through the surrounding space at thousands of kilometers per second. These waves compress gas clouds, trigger the birth of new stars, and at the same time destroy others that were forming. The result is a constant cycle of creation and destruction, a permanent turbulence that prevents the emergence of any stability. The gas heated by the explosions reaches temperatures of millions of degrees, becoming an incandescent plasma cloud that fills the galactic core with high-energy radiation. In addition to supernovas, stellar winds, continuous flows of particles emitted by massive stars, contribute decisively to the chaos of the center. These stars, dozens of times more massive than the Sun, release powerful streams of plasma that collide with each other, creating shock waves and violent magnetic fields. The result is a constant cosmic storm. The material expelled by these stars feeds the interstellar medium, but also interacts with the gravitational field of the central black hole, generating spirals of gas that heat up until they shine in X-rays and infrared. The combination of these forces creates what astronomers call a turbulent interstellar medium. It is composed of hot gas clouds, ionized plasma, dust, magnetic fields, and subatomic particles of extremely high energy. Space there is denser, hotter, and more dangerous than anywhere else in the galaxy. The average temperature of the gas near the center reaches millions of degrees Kelvin, enough to vaporize any solid material. No shield, physical or magnetic, could withstand that aggression for long. Another important effect of supernovas and stellar winds is the movement of gas toward and away from the black hole Sagittarius A star. Part of the material is drawn in and falls toward the nucleus, feeding the accretion disk and releasing even more energy. Another part is expelled outward, forming jets and radiation bubbles that extend for thousands of light years above and below the galactic plane. These structures, known as Fermi bubbles, are testimonies of the galactic center's past eruptions, gigantic scars of ancient explosions that still emit gamma rays today. The balance between these forces, gravity pulling in and explosions pushing out, is precarious and dynamic. The nucleus of the Milky Way lives in a state of constant instability. With each new supernova, the structure of the gas changes and new currents of matter are generated. This instability is what keeps the central black hole in an intermittent cycle of activity. During periods of calm, it remains dormant. During bursts of energy, it becomes a colossal source of radiation. Even tens of thousands of light years away, these activities influence the rest of the galaxy. The shock waves ejected from the center can travel vast distances, compressing interstellar gas and altering the rate of star formation in peripheral regions. Thus, the chaos of the core is not confined to it. Its consequences reverberate throughout the Milky Way, connecting the central regions to the outer ones through a delicate energetic balance. The study of these forces is carried out through telescopes that observe in multiple wavelengths: radio, infrared, ultraviolet, and X-rays, since none of these emissions are visible to the naked eye. The images obtained reveal a scenario that looks more like a battlefield than a center of balance. Explosions, jets, arcs of gas, and magnetic filaments cross space like scars of past events. It is in this extreme environment that the central black hole grows and the galaxy breathes, in cycles of destruction and reconstruction that define its evolution. Thus, the center of the Milky Way is the stage for a permanent war between gravity and energy. Supernovas and stellar winds are the armies of this war, shaping the destiny of the galaxy with every explosion. The result is an environment so chaotic that no civilization could survive in it. Life, which depends on stability, could not flourish where space itself is stirred by forces that are born and die at every moment. For this reason, the galactic nucleus is more than just a point of scientific observation. It is a reminder that the universe, in its beauty and magnitude, is sustained by forces that the human mind can only comprehend from afar. Every supernova that lights up the center is an explosion of power that at the same time destroys and creates. Chaos is the heart of the galaxy, and it is also what keeps it alive. The surroundings of the Milky Way's center are among the most paradoxical environments in the universe. They are at once a nursery and a field of destruction. Amid intense radiation, violent gravitational forces and constant turbulence, new stars continue to be born. This region, known as the central star-forming zone, is the most active in the entire galaxy, but also the most unstable. Whatever forms there is born condemned to a short existence. The giant molecular clouds that populate this area are immense reservoirs of gas and dust, with masses that can exceed millions of times that of the Sun. They are the fuel of stellar creation. Gravity causes these clouds to collapse upon themselves, generating the heat and density necessary for the birth of new stars. However, in the galactic nucleus, this process takes place under conditions completely different from those in the rest of the galaxy. Pressures are extreme, temperatures are high, and the environment is continually shaken by shock waves coming from nearby supernovas. This instability creates an accelerated cycle of birth and death. The stars formed in this region tend to be massive and short-lived, burning their fuel in just a few million years before exploding again as supernovas. Each new generation of stars adds energy to the existing chaos, feeding back the cycle of destruction. The result is a dynamic and turbulent equilibrium in which the birth of new stars is inseparable from the death of the old ones. The density of gas and dust also makes these regions practically impenetrable to visible light. What we know about them comes from observations in infrared, microwaves, and X-rays, which can pass through the dense layers and reveal the interior of these clouds. The images show clusters of young stars, rotating gas disks and jets of matter being expelled at high speeds. It is a scene of constant transformation, where gravity and pressure struggle to impose order amid disorder. The physical conditions around the center are so extreme that the very rate of star formation changes over time. In certain periods, there are intense bursts in which thousands of stars are born within a few million years. In others, the process slows almost completely when the energy released by supernovas and stellar winds disperses the gas needed for new formations. This intermittent behavior turns the galactic nucleus into a pulsing organism, alternating phases of calm and storm. The gravitational forces of the black hole Sagittarius A play a fundamental role in this instability. As gas clouds approach the center, they are stretched and fragmented by tidal forces. Some parts are swallowed by the black hole, while others are flung outward, feeding the accretion disk and generating energy jets. The material that survives is compressed and can give rise to new stars, a process that combines destruction and creation on a gigantic scale. These central stars formed under such extreme conditions are very different from those in the galactic disk. They are hotter, more luminous, and much more ephemeral. While the Sun will live about 10 billion years, a typical nuclear star may last only a few million before collapsing. This contrast shows how diverse the environment is within the same galaxy. On the outskirts, the pace is slow and stable. At the center, it is frenetic and violent. The instability of the nucleus's star-forming regions also has implications for the balance of the entire galaxy. Each supernova explosion and each plasma jet launched by these massive stars helps heat the interstellar medium and alter the distribution of gas. On large scales, this influences the rate of starbirth in other regions, as if the heart of the galaxy dictated the rhythm of the entire cosmic body. These regions are intensely studied by space telescopes such as James Webb and ALMA, which observe at wavelengths capable of penetrating interstellar dust. The data reveal a landscape of incredible complexity: whirlpools of rotating gas, plasma streams, twisted magnetic fields, and shock waves that travel hundreds of light years. Space there is a turbulent sea where every particle is in motion and every atom takes part in a constant battle between collapse and dispersion. Amid this chaos, life as we know it would be impossible. No planet could remain in a stable orbit long enough to allow the emergence of complex organisms. Intense radiation, continuous explosions, and variable gravitational forces would destroy any attempt at stability. The core of the Milky Way is a cradle that never stops giving birth, but never allows anything to grow. For this reason, astronomers often say that the galactic center is the ultimate example of order within chaos. It is the gravitational and energetic engine of the Milky Way, the point from which new stars arise and to which matter returns in an eternal cycle. It is the place where the universe shows that creation and destruction are faces of the same force. Gravity, the energy that builds the cosmos, and at the same time prevents it from breaking free. At the center of the Milky Way, stars do not move in smooth, regular orbits like the planets around the Sun. They follow chaotic, twisted, and unpredictable trajectories shaped by the colossal gravitational force of the supermassive black hole Sagittarius A, and by their constant mutual interactions. There, order is replaced by a chaotic ballet, where each star is both dancer and threat, spinning around a point that bends space-time itself. This region is known as the nuclear star cluster, a dense gathering of stars orbiting the galactic center at unimaginable speeds. Some of these stars travel at more than 8,000 kilometers per second, completing an orbit around the black hole in just a few decades. By comparison, the Sun takes 230 million years to circle the galaxy once. This difference in scale shows how extreme the core truly is, where time and motion acquire completely different meanings. The study of these orbits is one of the greatest triumphs of modern astronomy. Continuous observations over more than 30 years, mainly using telescopes such as Keck in Hawaii and the Very Large Telescope in Chile, have allowed scientists to track the movement of individual stars near Sagittarius A star. One of them, called S2, became a symbol of this research. It orbits the black hole in an extremely elongated elliptical path, approaching within just 17 light hours of the center. During this passage, it reaches speeds exceeding 25 million kilometers per hour, and its orbit directly confirms the presence of a massive, invisible object, the unmistakable signature of a supermassive black hole. The orbits of the stars in the core, however, are not stable. They suffer constant disturbances caused by mutual gravitational interactions and by the tidal waves of the black hole itself. With each close approach, space-time curves and the trajectory is slightly altered. Over thousands of years, these small variations accumulate, transforming elliptical orbits into chaotic spirals that can eventually lead to a star's destruction. Some are swallowed by Sagittarius A star, while others are flung outward at such high speeds that they completely escape the galaxy, becoming the so-called hypervelocity stars. This chaotic behavior is a classic example of what physicists call n-body dynamics, a system in which multiple massive objects interact gravitationally, creating trajectories impossible to predict over long periods. Even with modern supercomputers, it is not possible to calculate the exact future of these stars beyond a few hundred orbits. The system is deterministic in the laws that govern it, but unpredictable in outcome, a perfect portrait of the universe's complexity. The galactic center is also a natural laboratory of general relativity. The extreme proximity of the stars to the black hole makes them experience intense space-time curvature. Time passes more slowly for them than for distant stars, and their light is gravitationally redshifted when seen from Earth. These effects, predicted by Einstein in the early 20th century, were confirmed precisely by studying the behavior of the S2 star at its closest approach to the black hole. The stars that inhabit the core also face tidal forces so intense that many are destroyed before completing their natural life cycles. When a star comes too close, the black hole's gravity pulls its near side much more strongly than the far side, stretching it until it breaks apart. This process, known as a tidal disruption event, releases an explosion of energy that lights up the galactic center for weeks, a spectacle of destruction, revealing both the violence and beauty of the cosmos. The environment is so dense that stellar collisions are not rare events. In certain regions, the distances between stars are so small that close encounters occur frequently. These collisions can merge stars, create unstable binary systems, or eject one of the components at high velocity. The result is continuous gravitational chaos, a whirlpool of light and energy that defies any notion of stability. These conditions make the galactic core an impossible place for life, but an essential one for science. It is there that astrophysicists observe gravity in its purest, most intense form. Every distorted orbit, every burst of radiation, every bending of light is a clue to how the universe operates at its most extreme limits. The unpredictability of these trajectories is not an error of nature, but a demonstration of its complexity. The chaotic orbits of the core stars remind us that the universe is dynamic, unstable, and in constant transformation. While the Sun follows its calm orbit, 27,000 light-years away, the heart of the Milky Way beats in a violent rhythm, accelerating and destroying stars in endless cycles. This contrast shows how isolated we are in a privileged zone, far enough to exist, yet close enough to observe the abyss. In the galactic center, chaos is the rule and predictability the exception. It is there that gravity dominates all other forces and where motion ceases to be orderly to become dance. And it is precisely that dance, unpredictable and eternal, that keeps the galaxy alive. At the heart of the Milky Way, where stars orbit at unimaginable speeds and space bends under the force of the black hole Sagittarius A, there is a kind of vibration that can neither be seen nor heard, but that travels through the entire universe, gravitational waves. They are ripples in the very fabric of space-time, generated by extreme movements of mass and energy. Every collision between stars, every supernova explosion, and every gulp of matter by the central black hole produces small distortions that travel across the cosmos at the speed of light. These waves are literally the sound of gravity, the silent music of the universe. The theory of general relativity, formulated by Einstein in the early 20th century, predicted the existence of these waves as an inevitable consequence of a dynamic universe. For decades, they were only a mathematical hypothesis, until in 2015, the detectors of the LIGO Observatory in the United States captured for the first time the echo of a merger between two distant black holes. That moment was one of the most important confirmations in the history of modern physics, direct proof that space-time is elastic and can vibrate. At the center of the Milky Way, the conditions for producing these waves are ideal. The gravitational field is intense, the masses are immense, and the interactions are violent. When two neutron stars collide, or when a secondary black hole is captured by Sagittarius A, the energy release is so great that the resulting waves travel for billions of light years. Although these vibrations are almost imperceptible as they pass through Earth, compressing and stretching space by fractions smaller than the diameter of a proton, they carry with them information about the most extreme events in the cosmos. These gravitational waves do not propagate like sound waves in a physical medium. They are deformations of space itself. When a violent event occurs, it alters the curvature of space-time, and that alteration spreads like circles in a lake after a stone's impact. The difference is that the lake is the entire universe. In the case of the galactic nucleus, the events that produce these waves are constant: stellar collisions, captures of mass by the black hole, and gravitational disturbances among massive objects. The region around Sagittarius A is particularly rich in candidates for gravitational wave emitters. Small black holes orbiting the supermassive one, stars being slowly swallowed, and high-energy binary systems produce a symphony of continuous vibrations. These waves not only inform us about what happens at the center of the galaxy, but also help reveal details of the very structure of space-time. They are the cosmic equivalent of Earth's seismic waves. By studying them, scientists can map the invisible interior of the universe. Projects such as LISA, a space-based gravitational wave observatory planned by the European Space Agency, aim precisely to detect these emissions coming from the heart of the Milky Way. Unlike ground-based detectors, which capture higher frequencies generated by rapid collisions, LISA will observe long-period waves, those caused by massive objects moving slowly around supermassive black holes. When it is operating, it will be able to hear the echoes of the galactic center itself, revealing details that no telescope of light could ever see. These waves also serve as cosmic messengers of phenomena that leave no visual traces. In many cases, the collisions that produce them occur in environments completely shrouded in dust and gas, invisible in any band of light. But gravity cannot be blocked. Gravitational waves pass through everything, reaching us as direct signals of hidden events. Thanks to them, humanity can observe parts of the universe that were completely beyond the reach of traditional astronomy. Each detection is a window into the past. Because these waves travel at the speed of light, they bring us information about events that occurred thousands or millions of years ago. When a wave passes through Earth, it is as if we were feeling the distant pulse of the galaxy, the heartbeat of its invisible center. The oscillations are faint but constant, a reminder that space, though it seems silent, is always in motion. The galactic nucleus is a continuous factory of these vibrations. With each interaction, with each distorted orbit, small amounts of gravitational energy are released, adding up to a cosmic symphony that permeates the universe. No other region of the Milky Way generates such complexity of waves. They are the physical testimony to the chaos and beauty of the galactic center, the echo of gravity in its purest form. From a human point of view, these waves represent one of the few ways to hear the universe without relying on light. They show that the cosmos is not only visible, it is vibrant, and the fact that we can detect these vibrations coming from the heart of the galaxy is an impressive demonstration of humanity's ability to decipher the invisible. The gravitational waves of the galactic center, therefore, are more than a physical phenomenon. They are the living signature of the galaxy itself. They reveal that nothing is at rest, that space bends and unbends in eternal cycles. The entire universe vibrates, and each of these vibrations is a silent reminder that everything that exists is connected by gravity. Above and below the plane of the Milky Way stretch two gigantic, almost invisible structures that represent one of the most striking discoveries of modern astronomy. They are the Fermi bubbles, two colossal lobes of radiation extending 25,000 light-years in each direction from the galactic center. These bubbles are, in essence, energetic scars on the body of the galaxy, remnants of ancient and violent events that turned the heart of the Milky Way into a furnace of cosmic radiation. They were discovered in 2010 by the Fermi Space Telescope, specialized in detecting gamma rays. What scientists found was unexpected. Two symmetrical structures emitting extremely high-energy radiation stretching north and south of the galactic disk. No simple explanation fit that pattern. The bubbles were vast, homogeneous and intensely bright in gamma rays, the kind of radiation produced only by phenomena of extreme violence. The origin of these bubbles remains a matter of debate, but most evidence points to two main possibilities. The first is that they were formed by ancient eruptions of the supermassive black hole Sagittarius A. Millions of years ago, the Milky Way's core may have gone through a period of intense activity, during which large amounts of gas and dust fell toward the black hole. As this material was swallowed, it released colossal jets of energy that pierced the galactic disk, inflating the bubbles in opposite directions. The result was a pair of luminous wounds that still glow in the sky, echoing an ancient explosion. The second hypothesis suggests that the bubbles may have been created by explosive star formation at the galactic center. During periods of high stellar activity, thousands of massive stars are born and die in succession, releasing energy through supernovas and stellar winds. That combined energy would be enough to expel huge volumes of hot gas from the core, creating an expanding structure similar to the observed bubbles. Both hypotheses may be true. Perhaps the galactic center experienced a double fury, where the black hole and the supernovas worked together to reshape the surrounding space. The size and symmetry of the Fermi bubbles impress even the most experienced astrophysicists. Each contains energy equivalent to hundreds of millions of supernova explosions. The radiation they emit is so intense that, if visible, the night sky would show two immense luminous columns rising above and below the band of the Milky Way. Yet our eyes are not sensitive to gamma rays. We can detect them only with specialized instruments. Observations indicate that the bubbles are composed of ionized gas and relativistic particles traveling at nearly the speed of light. Along their edges, shocks and turbulence continue to heat the material, keeping the structures active even millions of years after their formation. They are not static. They continue to expand slowly, emitting energy and interacting with the surrounding interstellar medium. These cosmic scars reveal a violent, long-forgotten past of the Milky Way. The galaxy that now appears serene and stable was once the stage for colossal events. The Fermi bubbles are proof that the galactic heart is not only a gravitational force, but also a source of destructive energy. They remind us that the center of the galaxy has awakened before and may awaken again. Astronomers estimate that the bubbles formed between 3 and 6 million years ago, a period that coincides with the birth of new stars around the nucleus. This suggests that the galaxy underwent an explosion of activity that fed both the black hole and star formation. The result was a massive ejection of energy, a cosmic storm that permanently marked the structure of the Milky Way. Even today, the bubbles continue to emit gamma rays, and their interaction with the galactic halo produces streams of particles and magnetic fields stretching thousands of light years. These emissions are studied by space and ground observatories seeking to understand the role of these structures in the galaxy's evolution. They may, for instance, have influenced how gas is distributed in the halo, limiting the Milky Way's growth and determining its rate of star formation. The Fermi bubbles are, therefore, testimony to an explosive past. They are the energetic scars, revealing that the Milky Way was once far more active and violent than it is today. While we quietly orbit in one of its spiral arms, the space above and below us carries the memory of a time when the galaxy's heart burned like a giant star. These structures also serve as a reminder of our cosmic smallness. They show that even when everything seems calm, the universe still bears traces of events so powerful they defy human understanding. The Fermi bubbles are the marks of the Milky Way's ancient fire, the echo of an era when the galaxy breathed raw energy and was shaped by the uncontrollable forces of gravity and radiation. The spiral structure of the Milky Way is one of the most striking features of our galaxy, but also one of the most complex manifestations of gravitational balance in the cosmos. The spiral arms are not fixed structures, nor static sets of stars and matter. They are the result of gravitational density waves that propagate from the galactic nucleus, shaping the form and motion of everything that exists in the disk. And the center, with its supermassive black hole and its concentrated mass, plays a decisive role in maintaining this stability. Central gravity acts as the galaxy's invisible axis. The entire disk, composed of stars, clouds of gas, dust, and dark matter, rotates around this point, which is the nucleus. The force exerted by the center keeps stellar orbits aligned and prevents the disk from coming apart. Without this gravitational anchor, the Milky Way would lose its spiral shape and become a diffuse cloud of scattered matter. The galactic center is, therefore, the heart and the skeleton of the galaxy. The density waves responsible for the formation of the arms originate in part from gravitational fluctuations that arise from the nucleus. As the orbiting material moves, these waves propagate like tides in space, compressing gas and dust. This compression triggers the formation of new stars, which illuminate the arms and give them the luminous appearance we observe. The process is cyclical. New stars are born, shine, die, and release energy that keeps the waves in motion. Without the gravitational influence of the center, this cycle would become disorganized. The concentrated mass of the nucleus, which includes the supermassive black hole Sagittarius A star, the dense stars around it, and the nuclear star cluster, creates a deep gravitational field that stabilizes the motion of the galaxy's inner regions. This field serves as a reference point for the rest of the disk, defining the average rotational velocity of the stars and preventing the orbits from becoming chaotic. Even tens of thousands of light-years away, the Sun feels the pull of this center, and its motion is calculated in relation to it. On the other hand, the center is also a source of gravitational disturbances. The nucleus of the Milky Way is not an immobile point. It pulses, oscillates, and stirs due to interactions among its internal masses. These subtle variations generate waves that propagate through the disk, influencing the shape and spacing of the spiral arms. It is as if the galaxy's heart emitted gravitational beats, each of which reverberates to the most distant edges of the system. The stability of the arms depends on the delicate balance between differential rotation and central gravity. The inner regions of the galaxy rotate faster than the outer ones, which would tend to distort the arms over time. However, the presence of the nucleus and of dark matter corrects this tendency, keeping the density waves in phase and preventing the arms from unraveling. The result is a dynamic system that seems static on human timescales, but is actually in constant flux. Studies based on numerical simulations show that without the galaxy's central mass, the spiral arms could not be sustained for billions of years. The nucleus acts as a gravitational anchor that supports the spiral pattern. Even small changes in the mass of the center, such as the absorption of matter by the black hole, can alter the symmetry of the arms. This explains why galaxies with unstable nuclei often display distorted, fragmented, or asymmetric arms. The influence of the galactic center also manifests itself in another aspect. It regulates the pace of star formation along the arms. The flow of energy and matter that departs from the nucleus spreads across the disk, heating the interstellar gas and determining where new stars can be born. The spiral arms, therefore, are extensions of the central pulse, regions where the balance between compression and stability is momentarily achieved. It is as if the galaxy breathed. The nucleus inhales matter, the arms exhale stars. Even the Sun, located 27,000 light-years from the center, is influenced by this balance. Its orbit and the stability of the solar system depend on the constancy of galactic gravity. If the nucleus were to undergo a major disturbance, such as a merger with another black hole or a massive outburst of energy, the entire disk would feel the impact. The orbits of the stars would be altered, and the arms could gradually dissolve. This is why the heart of the galaxy is at once its most dangerous and most essential point. The Milky Way exists as we know it, because its center remains stable enough to sustain the gravitational dance that organizes everything around it. The nucleus and the arms are inseparable parts of the same system, connected by invisible forces that cross space. The balance between central chaos and spiral harmony is the secret of galactic longevity, and it is also the reason why human beings, on a small planet at the outskirts of an arm, can exist to contemplate the cosmos. The Milky Way, like all known galaxies, is not held together only by the gravity of the stars, gas and dust we can see. The force that keeps its structure cohesive and prevents it from dispersing is dominated by something invisible, which emits no light, reflects no radiation, and does not interact directly with ordinary matter. This mysterious substance is called dark matter, and it represents the invisible foundation upon which the entire galaxy rests. The discovery that something unseen dominated the gravity of the cosmos began in the 20th century, when astronomer Vera Rubin studied the rotation of spiral galaxies. She expected that in the outer regions, the stars would rotate more slowly, like the planets of the solar system, whose speed decreases with distance from the Sun. However, the measurements showed the opposite. The stars at the edges of galaxies rotated almost as fast as those near the center. This could mean only one thing. There was much more mass than could be seen. Since then, it has become clear that most of the Milky Way's mass is invisible. It is estimated that only about 10% of the galaxy is made of luminous matter, stars, planets, gas and dust, while the remaining 90% is dark matter. This substance forms a vast spherical halo that surrounds the entire galaxy, extending far beyond the spiral arms and the visible disk. It is this halo that keeps the stars bound to their orbits and prevents galactic rotation from tearing the structure apart. Dark matter does not interact with light, but exerts gravity. Through this gravity, it reveals its presence. It acts as an invisible framework, supporting the galactic disk and stabilizing the motion of the stars. Without it, the Milky Way would not exist as a cohesive structure. The outermost stars would drift into space, and the spiral arms would unravel over billions of years. Astronomers have managed to map the distribution of dark matter indirectly by observing the rotation of stars and the behavior of dwarf galaxies orbiting the Milky Way. The data indicate that the dark matter halo is gigantic, extending about 300,000 light-years and containing hundreds of billions of solar masses. This gravitational field acts as an invisible skeleton, sustaining the galactic structure and ensuring its dynamic stability. From a theoretical point of view, the exact nature of dark matter is still unknown. It may be composed of subatomic particles that interact only through gravity, known as WIMPs, weakly interacting massive particles, or other hypothetical entities such as axions or sterile neutrinos. None have been directly detected, but their gravitational effects are so evident that their existence is considered one of the pillars of modern cosmology. In addition to holding galaxies together, dark matter was essential for the formation of the universe as we know it. After the Big Bang, when the universe was a soup of energy and particles, dark matter began to clump first, creating gravitational wells that attracted ordinary matter. Galaxies formed within these wells, like leaves caught in invisible whirlpools. The Milky Way is one of those leaves, a vortex of ordinary matter shaped by the hidden structure of dark matter. Cosmological simulations show that the dark matter halo is neither smooth nor static. It has substructures, flows, and currents that constantly interact with the visible disk. These flows influence the velocity of stars, the shape of the spiral arms, and even the stability of the solar system. Everything that moves within the galaxy moves inside this invisible sea of gravity. Even the subtle movements of the sun and nearby stars reflect the influence of dark matter. Small variations in their orbits, gentle oscillations, and slight deviations result from interactions with the gravitational field of the halo. The Earth, the Sun, and all the stars are immersed in this invisible ocean, sailing through a constant gravitational tide that cannot be seen but can be felt in every curve of light and every stable orbit. The role of dark matter in the cohesion of the Milky Way is so fundamental that without it, the known laws of physics would not explain what we see. It is the cement of the cosmos, the link between the visible and the invisible, what prevents structures from collapsing and at the same time keeps them from dispersing. On a universal scale, it is the silent force that ensures the existence of order amid chaos. Though invisible, dark matter defines the shape, size, and destiny of the galaxy. It is the reason why the Sun and Earth can exist in stable orbits, protected by a gravitational balance that lasts billions of years. It is the invisible field that binds the universe together, the shadow that sustains all light. The Milky Way, despite appearing to be a fragile and scattered structure, is held together by a force we cannot see, touch, or directly detect, the dark matter halo. It is the invisible foundation that prevents the stars from drifting away from the galaxy and being lost in the intergalactic void. Without it, the spiral disk would slowly disintegrate, and the Milky Way would become merely a cloud of wandering stars roaming the universe. To understand its role, we have to imagine the galaxy not as a two-dimensional structure, but as a three-dimensional system wrapped by a gigantic gravitational sphere. This invisible halo extends for hundreds of thousands of light-years in all directions, far beyond the regions where there is light. While the visible disk of the Milky Way is about 100,000 light-years in diameter, the dark matter halo exceeds 300,000 light-years, encompassing not only the stars, but also the small satellite galaxies that orbit ours. The gravitational field generated by this halo is what keeps galactic rotation in balance. If we depended only on visible matter, stars, gas, and dust, the outer regions of the galaxy should rotate more slowly, and the stars at the edges would eventually drift away over time. But measurements show the opposite. Velocities remain practically constant across the entire galaxy. This is only possible because the dark matter halo adds invisible mass, providing the extra gravity needed to keep the stars bound to their orbits. This invisible gravity acts like a cosmic glue. Every star, from those orbiting near the nucleus to the most distant at the fringes of the disk, is immersed in this gravitational field. Even when the galaxy spins at enormous speeds, about 220 kilometers per second in the Sun's case, the halo's force prevents the centrifugal motion from flinging them outward. It balances the push of motion with the pull of gravity, maintaining overall cohesion. The halo also plays a crucial role in galactic formation and evolution. When the Milky Way was forming more than 13 billion years ago, dark matter began clumping before ordinary matter. Its gravitational concentrations created the first wells of attraction in the universe, and within them, visible matter accumulated, giving rise to the first stars and galaxies. Since then, the halo has continued to act as a stabilizing field, ensuring that the spiral disk remains bound and that newly formed stars are not ejected by internal instabilities. Without the halo, gravitational interactions among stars would cause slow but constant losses of orbital energy. Some stars would gain enough speed to escape the galaxy, while others would fall toward the center, altering the overall balance. In a few billion years, the spiral structure would dissolve. The presence of the halo prevents this process by distributing gravity uniformly, smoothing forces and balancing motion. The galactic satellites, such as the small dwarf galaxies that orbit the Milky Way, are also kept on their paths by the dark matter halo. They travel within this same gravitational sphere, bound by forces that extend far beyond luminous matter. In some cases, these satellites are slowly absorbed, contributing their stars and gas to the growth of the Milky Way. This merger process is possible because the halo acts as a gravitational damper, guiding trajectories and dissipating orbital energy over billions of years. Computer simulations that try to reproduce the formation of the Milky Way show that without the dark matter halo, the stars at the outer edges would have dispersed long ago. The visible disk, instead of being stable, would be turbulent and fragmented. The fact that the galaxy has kept its shape for so long is one of the most convincing pieces of evidence for the presence of this invisible field. The halo's influence also explains why the Milky Way interacts in an orderly way with its neighbors, such as the Andromeda Galaxy. Both are immersed in dark matter halos, and it is the interaction between these fields that will guide their future merger, predicted to occur in roughly 4 billion years. Even that catastrophic event will be controlled by the invisible gravity of dark matter, which will determine how the two galaxies fuse and what the shape of the new system will be. The halo, therefore, is more than a gravitational structure. It is the backbone of the galaxy. It maintains the balance between centripetal and centrifugal forces, supports the spiral shape, and ensures that the Milky Way can continue to exist as a coherent organism. Without it, the universe would be a much more dispersed place, dominated by chaos and fragmentation. Ultimately, the dark matter halo is what keeps the cosmos from falling apart. It is invisible, silent and intangible, but its presence is felt in every star that keeps orbiting, in every planet that follows its course, and in every galaxy that maintains its form. It is the Milky Way's invisible guardian, and one of the reasons why we will never leave it. The visible universe, with its stars, planets, nebulae, and galaxies, is only the illuminated surface of a much deeper reality. Everything we can observe represents less than 5% of the total content of the cosmos. The rest is made up of two invisible and mysterious elements, dark matter and dark energy. The first holds structures together, the second pushes them apart. Without dark matter, nothing we know would exist as it does. It is the cosmic scaffolding upon which the universe was built. After the Big Bang, the universe was a hot, uniform haze of energy and particles. There were no galaxies, stars, or planets, only radiation and scattered matter. In this homogeneous scenario, small density fluctuations began to appear, but they were far too tiny to form structures on their own. It was the presence of dark matter that allowed these variations to grow. Because it does not interact with light, it began to clump quickly, creating concentrations of gravity that acted as seeds for future galaxies. Ordinary matter, slower and subject to radiation pressure, was drawn into these invisible gravitational wells, and within them began to form the first stars. Without dark matter, the universe would still be a cold, diffuse sea of gas. Galaxies would never have formed, stars would never have been born, and light would never have spread through space. Dark matter was the foundational structure of the cosmos. It shaped the invisible and provided the mold upon which the luminous universe organized itself. The evidence for this fundamental role is abundant. The cosmic microwave background, the remnant heat of the Big Bang, contains patterns of tiny temperature variations. These fluctuations reveal the initial distribution of dark matter and show how it guided the growth of structures. Regions with higher dark matter concentration attracted more ordinary matter, accelerating the formation of the first galaxies. Without this influence, the universe would still be in a diffuse and dark state. Cosmological simulations performed on supercomputers confirm this essential role. When scientists create models of the universe without including dark matter, the result is an amorphous cosmos with no galaxies, no stars, and none of the complexity we observe. When dark matter is added, filaments, knots, and gravitational webs appear that reproduce exactly the distribution pattern of galaxies seen by telescopes. These simulations show that the visible universe is merely the luminous part of an invisible gravitational network that stretches across billions of light years. This network is known as the cosmic web, and in it, dark matter forms the main threads. Galaxies align along these gravitational lines like dewdrops hanging from an invisible spider web. Between the filaments lie vast cosmic voids, regions containing almost nothing but dark energy. Dark matter therefore not only shaped individual galaxies, but also the large-scale design of the universe itself. Without it, the Milky Way itself would not exist. The dark matter halo that surrounds it was the first component to form, and it still sustains its cohesion today. Dark matter ensured that stars could cluster, that planets could form, and that the sun could exist. It is a silent yet universal force, an invisible field that permeates everything that exists. The influence of dark matter also extends to the rhythm of the universe's expansion. Although it does not directly counteract dark energy, its gravity acts as a brake. slowing the separation of galaxies. Without this resistance, the cosmos would have expanded too quickly for structures to emerge. Thus, it not only created the visible universe, but also kept it cohesive enough for complexity to arise. Even though we cannot see it, dark matter reveals itself in every detail of the universe. It bends the light of distant galaxies, a phenomenon known as gravitational lensing, making its presence indirectly visible. It dictates the motion of stars, the shape of galaxies, and the way they cluster into groups and superclusters. It is the invisible force that organizes chaos and gives the universe its hierarchical structure. Without dark matter, the universe would be a place without form and without history. No star would have ignited, no galaxy would have taken shape, and no conscious being would exist to observe it. Dark matter is the invisible stage upon which the cosmic drama unfolds, and we are merely shadows dancing upon it. The irony is that, although it is essential, its nature remains a mystery. Scientists know what it does, but not what it is. It neither shines, reflects, nor absorbs light. It is a presence revealed only through the effects it has on what we can see. This lack of interaction makes it impenetrable, but also perfect for the role it plays, sustaining the universe without ever revealing itself. The visible universe is merely the reflection of dark matter. Everything that shines exists because something invisible holds it together. The cosmos is a luminous illusion built upon a framework of shadow, and it is that shadow that prevents everything from falling apart, the silent skeleton of infinity. The sun, although it seems motionless in the sky, is a constant traveler within the Milky Way. It moves at a speed of approximately 220 kilometers per second, following a stable orbit around the galactic center. This motion is neither random nor autonomous. It is dictated by galactic gravity, the collective force field created by the sum of the mass of the entire galaxy, stars, gas, dust, dark matter, and, at its heart, the supermassive black hole, Sagittarius A. The Sun is located about 27,000 light-years away from the center of the Milky Way, within the so-called Orion Arm, a relatively calm region between two major spiral arms. From this position, it completes a full orbit around the galactic nucleus every 230 million years, a cycle astronomers call a galactic year. Since its birth, about 4,600,000,000 years ago, the Sun has completed just over 20 revolutions around the galaxy. This motion is a direct result of the balance between two forces, gravity, which pulls the Sun toward the center of the galaxy, and angular momentum, which keeps it in orbital motion. It is the same principle that governs the movement of the planets around the Sun, but on an incomparably larger scale. The gravitational force that keeps it bound to the galaxy comes not only from the nucleus, but also from the mass distributed throughout the entire disk, and above all, from the dark matter halo that envelops everything. The Sun's path around the galaxy is not a perfectly flat line. It oscillates up and down relative to the galactic plane in a gentle vertical motion that repeats roughly every 70 million years. These oscillations make the Sun periodically cross denser regions of the disk, where there is a higher concentration of gas and dust. Some scientists speculate that these passages may be related to cycles of comet impacts and possible mass extinction events on Earth due to gravitational disturbances caused in the Oort cloud, the outer region of the solar system. Beyond this vertical motion, the Sun also undergoes small radial variations, drawing nearer to and farther from the galactic center over millions of years. This phenomenon, known as stellar migration, occurs because of gravitational interactions with giant molecular clouds and with the density waves of the spiral arms. The result is that the Sun does not follow a perfectly circular orbit, but a slightly elliptical and irregular trajectory, slowly drifting within the disk over billions of years. These motions, though imperceptible on human timescales, reveal how much the Sun is part of a larger cosmic dynamic. It is not at rest, it is bound to the Milky Way's gravitational current, sailing in a sea of stars that share the same fate. Each nearby star follows its own orbit, and together they form a vast rotating system in which gravity acts as an invisible conductor. Galactic gravity affects not only the Sun, but also determines the behavior of the entire solar system. All the planets, asteroids and comets that orbit the Sun are ultimately carried along by this motion. Thus, while Earth orbits the Sun itself and all the planets orbit the center of the galaxy. Earth's orbit is therefore just a small whirlpool within a colossal spiral. From a physical standpoint, the Sun's motion is governed by the laws of celestial mechanics. But on a galactic scale, it is also subject to the subtle forces of dark matter. The gravitational field of the halo influences the Sun's speed and helps keep its orbit stable over billions of years. Without this influence, the balance between centripetal force and angular momentum would be lost, and the Sun would end up being flung out of the galactic disk or pulled toward the nucleus. This balance is so precise that the Sun remains in an intermediate zone of stability, neither too close to the center, where gravitational forces and radiation would be fatal, nor too far away, where the matter density would be too low to maintain a coherent orbit. This position is a rare and vital equilibrium point. That is why the solar system inhabits a region known as the Galactic Habitable Zone, an area of relative calm where the conditions for life are possible. The Sun is therefore a prisoner of galactic gravity, but also a beneficiary of it. Its stable orbit has allowed life to develop on Earth without major external disturbances for billions of years. This stability is the direct result of the cosmic balance that governs the motion of the entire galaxy. With each lap around the nucleus, the Sun takes part in a universal choreography, a cycle of continuous motion that will repeat until the end of its existence. On cosmic scales, the Sun's motion is just one of many voices composing the Milky Way's gravitational chorus. It is one of 300 billion bodies that revolve under the influence of the same invisible field. And as long as that field exists, the Sun will continue its journey, obeying the force that shapes the destiny of all stars, gravity, the eternal bond between the visible and the invisible. The Sun's movement within the Milky Way is not limited to a simple orbit around the galactic core. It follows a complex trajectory, oscillating up and down relative to the galaxy's central plane, the disk where most of the stars, dust, and gas are concentrated. This motion, known as galactic vertical oscillation, is the result of the interaction between the galaxy's gravity and the Sun's orbital momentum. It is a kind of cosmic swing, in which the Sun slowly rises and falls, crossing the galactic plane at regular intervals over tens of millions of years. Astronomers estimate that the Sun crosses the Milky Way's midplane approximately every 35 million years, completing a full oscillation cycle, meaning one rise and one fall, every Mach 70 million years. This movement is caused by the uneven distribution of mass in the galactic disk. As the Sun orbits the center, the galaxy's gravity pulls it toward the plane, but the acquired momentum makes it overshoot that line, carrying it slightly above or below before pulling it back again. The result is an undulating trajectory, like a cosmic sine wave. During these oscillations, the Sun passes through regions of different interstellar densities. The central plane of the galaxy is denser in gas, dust, and stars, while the regions above and below are more rarefied. This difference can have subtle but profound consequences for the environment of the solar system. Some studies suggest that when crossing the galactic plane, the Sun passes through zones with a higher concentration of giant molecular clouds and interstellar dust, which may affect the amount of cosmic radiation reaching Earth and even influence climate cycles on geological timescales. There are even bolder hypotheses that link these oscillations to mass extinction events. According to this idea, when the Sun passes through denser regions of the galactic plane, the gravity of massive stars and giant clouds could disturb the Oort cloud, sending comets toward the inner solar system. This increase in impact frequency might be associated with periods of global destruction in Earth's history. Although this connection has not been definitively proven, it shows how the Sun's movement is deeply tied to the galaxy's dynamic structure. The Sun's oscillatory behavior is a direct consequence of the balance between gravity and inertia. The Milky Way's gravitational force tries to keep all stars in the central plane, but orbital motion creates vertical deviations that result in gentle oscillations. This phenomenon is common to all stars in the galactic disk, each following a similar trajectory with different amplitudes and periods. Together, these paths form a collective movement pattern that makes the disk appear to pulse slowly, as if it were breathing. Observations from the Gaia satellite, which precisely maps the motion of more than 1 billion stars, confirm that the Milky Way's disk indeed exhibits vertical gravitational waves. These ripples extend for thousands of light years and result from disturbances caused by smaller galaxies that interacted with ours in the past. The Sun, therefore, does not oscillate in a static space, but within a constantly moving medium, where the galactic plane itself bends and warps in response to cosmic forces. This vertical motion also has importance for the stability of the solar system. As the Sun crosses the plane, it encounters different intensities of radiation and particle density. These variations, though small on a human scale, can influence the amount of dust and gas interacting with the heliosphere, the magnetic bubble that shields the planets from interstellar radiation. This means that, over tens of millions of years, even Earth's natural protective barrier can fluctuate in strength, altering the cosmic conditions of the solar environment. The Sun's oscillating path is therefore a reminder that our solar system is part of a much larger dynamic. It does not move in a straight line, but dances with the galactic disk, following the rhythm of the gravity that shapes the entire Milky Way. This slow and steady oscillation is one of the most subtle manifestations of the interaction between the visible and the invisible, between the luminous mass of the stars and the gravitational field of the dark matter that permeates everything. On cosmic scales, this oscillation is just a detail, but it is also one of the reasons Earth exists in a stable environment. The Sun never strays too far from the galactic plane, nor approaches close enough to be consumed by the gravitational chaos of the center. It remains in an intermediate zone where life can thrive. Each rise and fall is a reminder that even the smoothest motions are part of a grand equilibrium, the same balance that keeps the galaxy united and the universe expanding. The Sun does not remain fixed at a single point in the Milky Way. It is a traveler that moves slowly through the galactic disk, crossing regions with different densities and conditions. Over its more than 4 billion year history, it has already traveled through various parts of the galaxy and in particular has crossed several of the spiral arms, the vast, luminous regions formed by young stars, clouds of gas, and dense dust. These crossings, which occur approximately every 150 million years, are dangerous milestones in the solar system's journey. The spiral arms and card of the Milky Way are like gravitational density waves that move more slowly than individual stars. This means that the Sun in its orbit crosses them periodically, like a ship passing through alternating bands of calm sea and storm. Within the arms, space is more populated by massive stars, supernovas, and interstellar gas clouds. Outside them, the environment is quieter and more stable, dominated by older, less active stars. These crossings can have profound implications for Earth's cosmic environment. When crossing a spiral arm, the Sun is exposed to much higher levels of cosmic radiation. Supernovas that occur in these arms launch waves of highly energetic particles and magnetic fields that propagate across thousands of light years. Earth, protected only partially by the heliosphere, can receive a considerable increase in cosmic rays, capable of altering the composition of the atmosphere and even influencing global climate on geological timescales. Beyond radiation, the bispiral arms are regions dense in giant molecular clouds, cold masses of gas and dust that can interfere with the Sun's heliosphere. When the solar system passes through these clouds, the solar wind can be compressed, reducing the natural protection against interstellar particles. This would make Earth more vulnerable to cosmic radiation and to possible changes in the flux of comets and asteroids. These interactions are subtle, but accumulated over millions of years, can have profound effects on Earth's biosphere. Some studies propose that mass extinction events on Earth may coincide with these crossings. When the Sun enters more active regions of the galaxy, the likelihood of nearby supernova explosions increases. A supernova within a radius of 30 light-years would be capable of destroying part of Earth's ozone layer, drastically altering the atmospheric chemical balance. Although such events are rare, their possibility reinforces the role of the galactic environment as a cosmic risk factor. Outside the arms, the Sun encounters periods of relative calm. These zones, known as interarm regions, are comparable to vast cosmic deserts. In them there is less gas, less dust, and fewer massive stars. It is in these regions that the solar system spends most of its time, protected from the energetic turbulence of star-forming zones. Currently, the Sun is in one of these quieter regions, the Kaki local arm band or the Orion arm tower, an intermediate band that offers enough stability for life to have developed on Earth. Astronomers believe that the next significant crossing of a spiral arm will occur in about 100 million years. Until then, the Sun will continue its silent path, orbiting the galactic center and gradually moving toward regions of higher stellar density. These migrations are inevitable, since the Sun does not follow a fixed track. It is constantly deflected by small gravitational perturbations, like a leaf carried by the current of a river that slowly changes course. From a physical point of view, the Sun's trajectory is determined by a combination of forces: the galaxy's global gravitational field, the density waves of the spiral arms, and local interactions with clouds and stars. Together, these create an irregular path, but one that is predictable on large scales. It is a gravitational dance of extraordinary precision, where every element of the galactic disk influences the others in an almost perfect balance. Crossing the spiral arms is also important for the key chemical evolution of the solar system. Each time the Sun passes through these regions, it is bathed in a new composition of dust and heavy elements produced by previous generations of stars. This cosmic dust, when captured by the solar system, enriches the planets with new materials, contributing to the chemical complexity that makes life possible. Earth therefore carries in its composition traces of multiple passages of the Sun through the arms of the Milky Way. The Sun's journey is, ultimately, a voyage through a gravitational ocean full of invisible currents and tides. Each crossing is a phase of this eternal cycle, where periods of calm and storm alternate on million-year scales. The Sun is a cosmic traveler bound to the Milky Way's current, moving slowly among the spiral arms under the silent command of gravity. And as the Sun continues its route, Earth accompanies it, carrying with it the fragility of life amid the galactic vastness. Each crossing is a reminder that the solar system is not isolated. It is part of a much larger organism, a living galaxy in constant motion. The Sun's path between the spiral arms is, therefore, humanity's own journey through cosmic time, a slow, dangerous, and inevitable crossing among the tides of the universe. At the center of the Milky Way, about 27,000 light-years from Earth, lies an object so powerful and enigmatic that it governs the dynamic destiny of the entire galaxy: the supermassive black hole Sagittarius, a star. It contains about 4 million times the mass of the Sun and serves as the gravitational nucleus around which all the galaxy's stars orbit, directly or indirectly. Although its immediate gravitational reach extends only a few dozen light-years, its presence is essential for the overall stability of the Milky Way. It is the invisible heart that sustains the galaxy's gravitational pulse. Supermassive black holes are the dynamic pillars of galaxies. They are born in the early stages of the universe, when dense clouds of gas collapse under their own gravity, fed by continuous growth through the fusion of stars and the absorption of matter. On cosmic scales, they function as centers of equilibrium, ensuring that the motion of surrounding stars remains stable. Sagittarius. A star fulfills this role silently, supporting the Milky Way's core and helping to maintain the orderly rotation of its disk. The influence of Sagittarius. A star manifests not only through its gravity, but also through its ability to regulate the energetic dynamics of the galactic nucleus. Even when dormant, it interacts with its surroundings. Small amounts of gas and dust falling toward it form an extremely hot accretion disk, emitting radiation and generating magnetic fields that affect the local space. This energy, though confined to the central region, helps stabilize the flow of matter in the core, preventing chaotic collapse of interstellar clouds and controlling the pace of star formation in that area. Moreover, the black hole serves as a gravitational anchor. It is the fixed point around which the galactic core revolves. Without this anchor, the central stars could disperse due to their intense mutual gravitational interactions. Sagittarius. A star acts as the center of mass that keeps the nucleus cohesive, preventing the extreme density of that region from turning into destructive instability. Its presence gives the galactic heart a lasting, though chaotic, structure. Decades of observations with high-precision telescopes, such as the Very Large Telescope and the Keck Observatory, have revealed the direct effects of Sagittarius, a star's gravity. Stars near the center, known as S-stars, orbit in elongated ellipses at speeds exceeding thousands of kilometers per second. One of them, called S2, recently completed a full orbit around the black hole in just 16 years. The behavior of these stars not only confirms the presence of a supermassive object, but also demonstrates how the gravity of Sagittarius, a star, shapes the galactic core and influences the stability of the Milky Way's disk. Even on larger scales, the role of Sagittarius A star remains crucial. The gravitational field of the nucleus helps dampen oscillations in the disk, and preserve the galaxy's average angular momentum. It acts as a gravitational reference point, aligning the collective movement of stars and ensuring that the system remains stable over billions of years. This stability allows the Milky Way to maintain its spiral shape and avoid distortions that could destroy it. However, the black hole's influence has limits. It does not control the motion of all the galaxy's stars. That function belongs on a larger scale to the dark matter halo that envelops the Milky Way. Still, the black hole serves as a catalyst for internal balance. It is the central mass that organizes local chaos, ensuring that the core remains functional even under the constant pressure of crossing forces, supernovas, stellar winds, and streams of gas. Episodes of intense activity from Sagittarius, a star, such as the energetic eruptions that created the Fermi bubbles millions of years ago, also played a key role in regulating the galaxy. These eruptions may have cleared excess gas from the core, temporarily reducing the star formation rate and preventing the center from collapsing under its own weight. It is a kind of natural self-regulating mechanism. The black hole feeds and then releases enough energy to restore the system's balance. From a cosmological perspective, supermassive black holes appear to be a common feature of all massive galaxies. This suggests that they are a fundamental component of the universe's engineering itself. Without them, galaxies would be unstable and short-lived, incapable of maintaining coherent structures for billions of years. Sagittarius, a star, therefore, is not merely a curiosity at the Milky Way's heart. It is the key to its longevity. Ultimately, the central black hole is the Milky Way's gravitational guardian. It represents the boundary between creation and collapse, the point where gravity reaches its limit and time nearly stops. Without it, the galaxy would lose its balance. With it, chaos is organized into harmony, and the Milky Way continues to spin, silently, for billions of years. The idea of crossing the boundaries of the galaxy has always fascinated the human imagination. In works of science fiction, ships travel millions of light years in an instant, jumping between stars and galaxies as if space were a navigable ocean. But in reality, galactic gravity imposes insurmountable limits. The Milky Way is a system of 300 billion stars held together by a colossal gravitational field, and escaping that field is, from a physical standpoint, practically impossible for any conceivable form of life or technology. The gravity of the galaxy acts as an invisible prison. Just as a planet holds its satellites and a star holds its planets, the Milky Way keeps all its stars, systems, and nebulae trapped within its sphere of influence. To escape that attraction, an object would need to reach galactic escape velocity. In the Sun's neighborhood, that speed is approximately 550 kilometers per second, almost twice the rotational speed of the solar system around the galactic core. No human spacecraft has ever come close to that. Even the fastest probes ever launched, such as Voyager 1 and Voyager 2, travel at about 60 kilometers per second relative to the Sun. At that speed, they would take tens of millions of years to cross the galaxy, and would still remain bound to it. The combined gravitational force of all its mass, stars, dark matter, and the central black hole ensures that nothing originating here can simply leave the Milky Way. But the obstacle is not just speed. It is also the energy required to escape. The kinetic energy needed to accelerate a spacecraft to a significant fraction of the speed of light is gigantic, far greater than all the energy produced by our civilization throughout its entire history. And even if it were possible, the interstellar medium, seemingly empty, would be lethal. A collision with a single hydrogen atom at such speed would release energy comparable to that of an explosion, destroying any ship. Moreover, the galaxy is an intricate gravitational web. The influence of dark matter extends far beyond the visible disk, and its gravitational halo prevents stars and their systems from escaping spontaneously. This halo acts as an invisible wall. The farther a ship tries to go, the more energy it needs to overcome the residual pull. It is a physical and mathematical limit, a frontier that cannot be crossed without violating the laws of relativity and energy conservation. Even within the galaxy, interstellar exploration faces immense challenges. The distances between stars are abyssal. The nearest one, Proxima Centauri, is more than 4 light-years away. At Voyager's speed, the trip would take 70,000 years. Even with theoretical technologies, such as laser sails or fusion propulsion, travel time would still be measured in centuries or millennia. Space is too vast, and human time too short. These limitations make the idea of leaving the galaxy not only a technological impossibility, but also a conceptual one. The Milky Way is such a large and deep gravitational structure that any being or civilization born within it is inevitably bound to remain inside its limits. Stars may die, planets may vanish, but their ashes will remain trapped within the galactic field. Even hypervelocity stars, ejected from the Milky Way by close interactions with the central black hole, are rare and violent exceptions. They reach enormous speeds and can escape the galaxy, but only at the cost of destroying their planetary systems and losing stability. They are cosmic projectiles, not travelers. No civilization could exist or survive in such an extreme event. Galactic gravity is also tied to the very fabric of space-time itself. The curvature of space within the Milky Way is shaped by the distribution of its total mass. To escape that curvature, one would need to distort space itself, requiring energies comparable to that of the entire universe. Not even exotic matter theorized for superluminal drives could achieve such an effect without violating the fundamental laws of physics. That is why interstellar exploration within the galaxy is already by itself an almost impossible feat on human scales. Escaping the galaxy would be even more so. Gravity, silent and relentless, keeps everything together, not as an arbitrary prison, but as a natural balance. Every star, every planet, every grain of dust is part of this harmonic system that has endured for billions of years. The dream of leaving the Milky Way is therefore more philosophical than physical. It represents humanity's desire to transcend limits, but nature itself has imposed a final boundary. We may travel between worlds, explore stars, and even understand the universe, but we will never leave the galaxy that gave us birth. We are children of the Milky Way, and its gravity is our inheritance. As long as it exists, we are bound to it, not by chains, but by geometry, not by force, but by origin. And that connection makes the galaxy not only our prison, but also our eternal home in the cosmos. Throughout the universe, the laws of physics follow an absolute principle. Nothing that has mass can reach or surpass the speed of light. This limitation imposed by relativity is the first and most fundamental obstacle to any attempt to escape the Milky Way. Even if a spacecraft could achieve a significant fraction of that speed, the time and energy required would be immeasurable. And intergalactic space, the void between galaxies, would be a journey lasting hundreds of millions of years. The galaxy, with its immense gravity, keeps us within a field from which not even light, if it were trapped, could easily escape. The final boundary of the Milky Way is not a physical wall, but a gravitational and energetic frontier. The galaxy is surrounded by a vast halo of dark matter, whose influence extends for hundreds of thousands of light years. This halo not only holds the stars together, but also defines the radius of the galaxy's gravitational influence. Within it, everything that has mass is part of the galaxy's dynamic system. Beyond it, space becomes the realm of the intergalactic void, where the gravity of other galaxies begins to compete for attraction. Escaping this boundary would be like trying to climb an infinite mountain, where each step requires more energy than the previous one, until the effort becomes physically impossible. Even hypervelocity stars, the only ones known to reach the edge of the galaxy, demonstrate this limit. They are expelled by extreme events near the central black hole, where violent gravitational interactions hurl them at speeds exceeding 1,000 kilometers per second. Some manage to escape the Milky Way, but they do so without planets, without systems, without stability, merely as isolated fragments launched into the void. They do not flee the galaxy as travelers, but as debris of gravitational collapse. They are reminders that exit is possible only at the cost of destruction. Beyond gravity, there is another, more subtle limit: cosmic time. The Milky Way is a system that renews itself, but also evolves slowly. In about 4 billion years, it will collide with the Andromeda galaxy, merging into a new elliptical structure. During this process, the stars will change positions, the spiral arms will vanish, and the combined gravity will form a new core. Even if an advanced civilization existed in that distant future, it would still be trapped within the same expanded gravitational field, a new galactic empire from which there is no escape. The expansion of the universe itself reinforces this confinement. As space stretches, galaxies move away from each other at ever-increasing speeds. In a very distant future, all galaxies beyond the local group, the small cluster that includes the Milky Way, Andromeda, and several dwarf galaxies, will disappear from the observable horizon. This means that even if we could travel at the speed of light, we would never reach other galaxies, because the very fabric of space between them would expand faster than we could traverse it. We will be, inevitably, confined to our local universe. In energetic terms, galactic gravity creates a well so deep that completely escaping it would require converting impossible quantities of mass into energy. Even with advanced relativistic propulsion theories, such as antimatter engines or fusion drives, the energy required to cross the galactic halo exceeds the combined output of all the stars in the Milky Way. Total escape is not merely improbable. It is forbidden by the laws that govern energy conservation and the curvature of space-time. The ultimate boundary is, therefore, the very structure of the universe. The Milky Way is a cell in a larger cosmic organism, and each cell is isolated by the invisible barriers of gravity and expansion. We exist within this system, born from its dust and shaped by its energy. Everything we know, the sun, the earth, the planets, life itself, belongs to this galaxy. There is nowhere to escape to, for beyond it there is no shelter, no light, and no energy sufficient to sustain existence as we know it. This limitation, far from being a prison, is also a form of balance. The galaxy is both the cradle and the grave of all that exists within it. The same gravitational field that prevents escape is the one that keeps the sun in orbit, that shapes the spiral arms, and that sustains the cycle of birth and death of the stars. The impossibility of escape is the price of stability. Thus, the final boundary is not only physical, it is also philosophical. It reminds us that even before infinity, we belong to something. The Milky Way is our origin and our destiny, and as long as gravity exists, we will remain part of its structure. When the sun dies, its ashes will continue to orbit the galactic center. When Earth vanishes, the atoms that once formed human beings will disperse through space, yet still within the galaxy that created them. Nothing completely escapes the Milky Way, neither matter nor light, nor the memory of what once was. In the end, everything returns to the same point of origin, drawn back by the silent force that keeps the universe united. The galaxy is not only our home, it is the ultimate limit of what is possible. Over billions of years, the universe has shaped the Milky Way into a living, complex, self-regulating structure. It is a cosmic organism made up of hundreds of billions of stars, of the invisible dark matter that binds them together, and of gravity that coordinates every motion. And within this system, the sun, the earth, and everything we know are merely particles in a colossal mechanism, silently revolving around a core we will never see up close. What we have learned is that the Milky Way is not just a collection of stars, it is a natural gravitational prison. Its spiral structure is maintained by forces that cannot be overcome. Dark matter forms the invisible skeleton that prevents the stars from dispersing, while the central black hole, Sagittarius A, acts as an anchor and dynamic regulator. Each element is bound to the other by a precise equilibrium, and breaking that balance would require defying the very laws that uphold the cosmos. On its journey, the sun follows a stable orbit, gently oscillating through the galactic plane, crossing spiral arms, avoiding regions of chaos and radiation. Each crossing is proof of the force that keeps it bound to the Milky Way. Even on astronomical scales, its path never carries it outward. It only makes it circle an invisible center, like a leaf in an eternal whirlpool. The galaxy's gravity is so deep that to escape it, one would need to reach speeds above 500 kilometers per second. No machine built by humanity has reached even a tenth of that. And even if a civilization achieved such a feat, the energy required would be comparable to that of all the stars combined. The price of escape would be collapse itself. But confinement is not a punishment. It is a natural consequence of the universe's structure. The Milky Way is a microcosm within a larger network, connected by webs of dark matter stretching across billions of light years. Each galaxy is a cell, isolated by gravitational boundaries and by the accelerated expansion of space. To flee a galaxy would be the same as trying to escape the geometry of space-time itself. Dark matter, silent and invisible, sustains the cosmos. Without it, there would be no galaxies, stars, or planets. It is what maintains the coherence of the visible universe, what gives shape to the infinite. The same holds for dark energy, which pushes space outward and defines the limits of the cosmic horizon. Together, these forces create the stage on which life exists, and at the same time ensure that it remains confined within a precise scale. At the heart of the Milky Way, Sagittarius, a what keeps turning, feeding on matter and returning energy to space in invisible bursts. Its power keeps the galactic nucleus in balance and indirectly contributes to the stability of the disk where we live. It is the symbol of the cosmic paradox, the force that attracts everything and the limit that preserves everything. When we look at the night sky, we see only a small fraction of this reality. The stars that shine are fellow travelers, bound to the same fate as the sun. Each one follows its own orbit, obeying the same universal law. The space between them seems empty, but it is filled with currents of gravity and the invisible presence of dark matter. Nothing is truly at rest. Everything moves around a center that no one can abandon. Even the most advanced civilizations that may arise, here or elsewhere in the galaxy, will be subject to the same limits. Intergalactic space is cold, vast, and inhospitable, a crossing that lasts millions of years, where not even light survives without fading. There is no escape route that can overcome the expansion of the cosmos, nor any engine that can surpass the galaxy's gravitational frontier. The Milky Way is not just our home, it is our final horizon. Ultimately, we will never leave the Milky Way because we are part of it. Our origin lies in the stars that were born within its arms. Our matter was forged in the supernovas that once illuminated its past, and our future is written into its slow, eternal rotation. Even when the sun fades and the Earth disappears, their atoms will continue to orbit within this system, mingled with the cosmic dust that will one day give rise to new stars. The impossibility of escape is, paradoxically, the reason for our existence. It is confinement that allows balance, the limit that makes the universe comprehensible, and gravity that turns chaos into order. The Milky Way is not a prison. It is the cosmic cradle where life, light, and time meet in harmony. And as long as the universe continues to expand, we will keep spinning silently within it, inseparable from the spiral that gave us birth. Because in the end, no one leaves the Milky Way. Everything is born within it. Everything dies within it. And everything remains eternally under the dominion of the gravity that binds infinity together. If you've made it this far, take a deep breath. Now close your eyes and imagine the exact place in the Milky Way where the sun is, spinning silently for billions of years. You are part of that. Every breath, every thought, every fragment of your body was born within this galaxy, and it is here that it will continue to exist even when time erases everything we know. If this journey through the Milky Way made you think, tell me, where in the world are you watching from right now? Leave a comment with the name of your city or country. It's incredible to see where this cosmic community connects from. Also, don't forget to like this video, subscribe to the channel and activate the bell. That way, you help this project continue creating long, dense and tranquil content like this, to listen, learn and fall asleep under the sound of science. And if you want to keep traveling with me, just leave in the comments which topic you'd like to explore in the next episode. It can be something about the universe, time, life, or the future. The next step of humanity might begin with your suggestion. Thank you for staying until the end.